Okay, welcome to this video where we are having a look through the topics that have appeared on the advanced information that the exam board has released for the 2022 Maths GCSE. We're going to be looking at higher paper 1 in this, and as you can see on the screen, I've done a list here, or a checklist, for all of the topics that are on the advanced information for that paper 1. Now, I have actually done this checklist for all of papers 1, 2 and 3, and if you'd like to have these or you'd like to download them and print them off, you can get them in the description, and I'll show you that in just a moment. So these are free for you to download, use them as you want, give them to your friends, but that's completely up to you. Now obviously, if you've been following this channel for a while, you'll know exactly how these videos work, but just in case you're landing here for the first time, I'm going to show you how it works, and I'm going to show you obviously how you can get to this file. So let's have a look at that now. So when you're on one of my videos, if you pause it to start with, you can click onto the chapters on the bottom left, and you'll see that I have bookmarked all of these topics that are on the list in order that I've drawn them on the list, so that you are able to go through and pick the topics that you want. As well as that, if you go into the description, you will see there that in the description there is a link where it says the Higher and Foundation Revision Checklist, where you can download that checklist that I was just showing you. Just below that will be all the links to all the different papers, so you can access all the papers and have a look through the videos, but just remember, obviously I'm only going through one version of each topic, so you will have to look further in depth into each of these topics, as I'm only going to be covering one small snippet in a much larger topic. So if you scroll down, you'll also see that I will have all the links next to these timestamps. This particular video, haven't actually put them on just yet, but hopefully by the time that you're watching this, all of the links will be on there. As you can see there, at 1 hour and 11 minutes, you can see the exact values of trigonometry video is there, so you can always click into that and have a look at the full video, and that is obviously how this video works. So hopefully that's useful and helpful. If these videos are useful, please don't forget to like the video, don't forget to subscribe to the channel so that you get all the updates for all the future videos, and don't forget to drop me a comment and let me know if there's anything else that you'd like making, or just to let me know obviously how it's all going throughout the course of the year. Right, we've got a lot to get through, so let's get started. Okay, so this question says 3/5 of a number is 48, work out the number. So this really tends to confuse people when it does come up, because obviously when you see 3/5 of a number, a lot of people are going to think, okay, straight away divide by the bottom times by the top. But this is actually in reverse. This is saying that 3/5 of a number is already 48. And if we think about this in terms of our bar again, let's just think about if we had split this up into 5 portions this time, because it is in terms of fifths. There we go. So if I split this up into 5 parts, which I may not get perfect, there we go, good enough. And what it's saying is that 3 of them has already been calculated as 48. And we want to know what the entire original number is. So looking at this then, okay, well, if only 3 of them were 48, well, we wouldn't divide by 5 anymore, but instead we would divide by 3, because we want to know how much is going to go into each of those 3 boxes just above. So this time, and it's obviously the complete reverse of before, because this time we're going to divide by that numerator. So instead we're going to divide it by 3, and that's going to tell us what number goes into each of the bars above. So 48 divided by 3 is equal to 16, and again you can put that, obviously the working out, just to the side. So if I put now 16 into each of these bars, I would also put it into those additional 2, because we are looking at now all 5 of them. So that number there, if we add up all of those 16s, and again, you can obviously add them all up, or you can do 16 multiplied by 5. So that working out, I would do to the side, 16 times 5, because there are 5 boxes, and that adds up to 80. There we go. And that is my answer. And again, you could put the 80 next to your diagram if you prefer to use a diagram method, but that is how we're going to go about approaching these questions. So if you think about what we've actually done, it's just the complete opposite of what we did before, and that's why it's in reverse. This time instead we are dividing by the numerator and multiplying by the denominator. but you need to understand why, and I think that this visual idea really does help you to understand why we would divide this time by the numerator and why previously we were dividing by the denominator. So for the first one, we've got work out 3 4/5, add 3/7 and give your answer as a mixed number in its simplest form. Now when we're looking at this sort of question here, one thing that we need to remember, no matter which type of calculation we're doing, adding, subtracting, dividing or multiplying, if we have mixed numbers involved, we need to make them top heavy first. Now when it comes to adding and subtracting, there is a little bit of a different approach that you can take that some of you may use, but I'm going to use the same method for all of these types of questions, and that is making any mixed numbers top heavy fractions first, or improper fractions first. So the process for doing that is obviously taking our fraction here, 3 4/5, we want to turn that into an amount of fifths. So to do that, we want to figure out how many fifths are in 3. So we can do 3 times 5, which is 15. Add the extra 4/5 there, and that makes 19 fifths. So 3 4/5, 3 times 5 is 15. Add the 4 that we've got there as well is 19 fifths. Okay, so it's the big number times the bottom to make 15, add the top number on the fraction there, 19, so we've got 19 fifths. And we're going to add that to the 3/7. Now when it comes to adding and subtracting, we need to have a common denominator. So we need that number on the bottom to be exactly the same. Now that means that we can multiply both fractions here. As long as we do whatever we do to the bottom, we also do to the top. We can make equivalent fractions with a common denominator. So thinking about 5 and 7, the lowest common multiple of those is 35. So in order to get them to be 35, the left fraction there, I can times the top and bottom by 7. And the right fraction we can times the top and bottom by 5, and that would give us 35 on the bottom of both. So we've still got to work out 19 times 7 there, and obviously take your time doing so, but 19 times 7 is 133, and at the moment that is going to be over now 35. Okay, so you get some quite big numbers here, but obviously don't be afraid just to the side to do some multiplication there. I did 7 times 10, and 7 times 9, and added them both together, okay, but you can show you working out to the side. On the right fraction there, we're going to times them both by 5, so 3 becomes 15, and 7 becomes 35. And now we're in a position where we can add these both together. So we can just add together the numerators, 133 plus 15, which gives us 148, and that is over 35, remembering that you don't add together the denominators. There we go, we've got 148 35ths. Now obviously it says here to give your answer as a mixed number in its simplest form. So it's up to you whether you try and simplify this or whether you so obviously turn it into a mixed number first, but we need to turn it back into a mixed number. So to do that I need to know how many times does 35 go into 148. That's not the nicest, so I'm just going to write down a few of the 35 times table. So 35, add another 35 is 70, add another 35 is 105, add another 35 is 140, and then it's not going to go beyond 140 there, because obviously our number there is only 148. So to go from here, we know that 35 goes in 4 times, so that's going to be a big 4. And what's left over from 140 to 148 is an additional 8 35ths. There we go, so 4 and 8 35ths left over. Okay, so looking at that number there, you've just got to decide as well, does that little fraction at the end there simplify? Does 8 over 35 simplify? Now in the case of this fraction here, it actually doesn't. There's nothing that goes into both 8 and 35 other than 1, and obviously that's not going to simplify it for us. So that actually is fully simplified there. So even though it says give it in its simplest form, in this circumstance here, that little fraction on the end there doesn't simplify, okay? But it's going to say that anyway, because we didn't have to use 35 as our denominator. We could have potentially used a bigger number like 70 or even larger if we wanted, but because we used the lowest common multiple, it's just ended up that doesn't actually simplify at the end there. But do look out for that, because that fraction quite often does need simplifying, okay? But there's our final answer, 4 and 8 over 35. Right, okay, so dividing with mixed numbers to start with. It says, so work this out, 1 1/5 divided by 3/4, give your answer as a mixed number in its simplest form. So again, let's make these top heavy. So 1 1/5 is 6/5, big times the bottom is 5, add the 1 is 6, and we're going to divide that by 3/4. Okay, now normal fraction rules apply here. When we are dividing fractions, we keep the first one as it is. We're going to flip the second one over, do the reciprocal of that second one, and then we're going to multiply the fractions instead. And multiplying fractions is probably one of the easiest little bits of math you ever have to do, because you know exactly what we'd like to happen happens. We just multiply the top, multiply the bottom. So in fact, rather than doing 6/5 and doing a divide, I'm just going to times it by the reciprocal, which is 4 over 3, literally just flipping it over. And then from there we just multiply the top numbers. So 6 times 4 is 24, And 5 times 3 is 15. And there we go, we get our final answer. And obviously it says to give your answer as a mixed number in its simplest form, so I do want to have a look at creating a mixed number or simplifying it first. Okay, it's up to you which one you go. I'm going to turn it into a mixed number first, so we get 15 goes into 24 once, so we have 1, and the remainder there is 9 from 15 to 24, so we have 9 over 15 left over. Now this is the first time this has come up, look, because that mixed number there, okay, this little fraction with it does actually simplify. They both divide by 3. And I would need to simplify this now. Okay, so that would end up being 1. And if I divide the top and bottom by 3, 9 divided by 3 is 3. And 15 divided by 3 is 5. So my final answer is 1 3/5. Okay, so you just got to spot and watch out for that, okay? But there is something else you could have done. You could have taken a slightly different approach there. You could have actually simplified at this point. The top and bottom both divide by 3 and you get 8/5 when you do that. And then you could turn it into a mixed number from there. So 5 goes into 8 once, with a remainder of 3, and you get 1 3/5. So it's completely up to you which method that you prefer to use, whether you turn it into a mixed number first and simplify the fraction, or whether you simplify the fraction and then turn it into a mixed number. It's completely up to you. Okay, but just obviously remembering that when you divide, you keep the first one and you multiply by the reciprocal. Okay, and a lot of people remember that like keep, flip, change. Okay, you keep the first, flip the second, and change the sign into a times. And obviously when we're multiplying fractions, that's really nice and easy. So it says write 0.47 with the recurring dot above the 7 as a fraction in its simplest form. Now when it comes to this, we are going to use a bit of algebra to do so. Now the first thing we're always going to do is just write that x equals the decimal in the question, 0.47, the recurring dot. And it's important just to think about what's actually recurring here, and it's just the 7. If I was to write it out as an actual decimal, it'd be 0.4, and then I could just keep writing 7s forever. Okay, now when there's only one recurring decimal, the thing that we can do here is if we can take this value of x, which is 0.47, we can just multiply that by 10. And depending on how many recurring decimals there are, will determine what we actually want to multiply it by. And you'll see the reason that we actually do this. So if we multiply it by 10, we would get 4.7, and then it'd be another 7 as it's recurring. And I'm not going to write any more 7s, I'm just going to write the same amount of decimal places as I have in my one above there. 2 decimal places in 0.47, so I'll keep 2 decimal places in this version here. Now the reason this can help us is now we can take these away from each other. And if we do take them away from each other, those recurring 7s are going to cancel out. So I want to take them away, and it can seem a little bit odd doing this because I'm doing the bigger number on the bottom, take away the smaller number on the top. So you can always feel free to realign it to the side, which I can do over here. I won't actually normally do this, but 4.77, take away 0.47. Okay, so I tend to do it just looking at it sort of upside down on the side, but you can actually just realign it. Look, the 7 take away the 7 makes 0, the 7 take away the 4 makes 3, and then 4 take away 0 is 4, so it's 4.3. So when we take these away from each other, 10x take away the 1x leaves us with 9x, and then our decimals, when we take them away, we get 4.3, and I won't write the 0 after that, I'm just going to write 4.3. Now there are other methods of doing this. This is just the way that I like to do it. I always just like to remember one recurring decimal, multiply it by 10, and then take them away from each other. But you end up with this scenario here, look, where we have a decimal on the right hand side. We've got 4.3. Now I can't turn this into a fraction, or I could, but we shouldn't really have decimals in a fraction. So before I turn it into a fraction, I'm going to multiply both sides by 10. So once we've multiplied both sides by 10, we get 90x, and that equals 43. And now we can turn that into a fraction. We've got 90 in front of the x, so we can divide both sides by 90. And it's important to leave this in terms of algebra because some of these questions will say prove, so I'm just going to keep it as x equals. So x equals 43 divided by 90, or over 90. There we go. Now we've almost finished. It does say give it in its simplest form. Now you've got to think, does this fraction actually simplify? Okay, so there are different ways of actually doing recurring decimals, and sometimes you might not get it in its simplest form. Now the way that I have done it does actually leave this fraction here in its simplest form. Okay, 43 over 90 doesn't simplify. It is worth just having a check though, just try and apply some little tricks. Are they both even? Do they both divide by 2? Do they divide by 3 or 5? And keep just checking a few numbers that you know go into 90. possibility. But as the way I've done this particular question, it has actually finalised in its simplest form. Okay, so that one doesn't actually need simplifying, but just make sure you check in those final steps to see if it simplifies. Okay, 525 is a product of prime factors. So with these slightly harder numbers, we're going to try and apply some number tricks here. So let's have a look. What does that divide by? Now, things that I'm spotting, it ends in a 5, so it definitely divides by 5. And it ends in this 25, so it does also divide by 25. Now I'm going to just stop to divide by 5, because I can do that quite easily over to the side. And don't be afraid to do some working out for these. So 5's into 5 goes once, 5's into 2 doesn't go, so carry that over. 5's into 25 goes 5 times. So 525 is a little split there, is 5 times 105. And again, 105 ends in 5, so we can do the same again. You might be able to do some of them in your head, but I'm just going to show you obviously that you do have these methods available. 5 doesn't go into 1, 5 goes into 10 twice, and 5 goes into 5 once. So 105 is 5 times 21. Now we're at a point here where hopefully we spot that 21 is 3 times 7. And there we go, we've finished off our tree. So we've got 5, 5, 3, and 7. So 3 times 5 times 5 times 7. And then putting these two 5s as 5 squared. So 3 times 5 squared times 7. So this first one, we've got 25 to the power of negative a half. Now when it comes to these powers, we just need to remember what each piece does. So if we make some notes on this, the negative part of the power, as we've seen before, does the reciprocal. It flips it over. So it flips it over. The number on the bottom, underneath that line there, which I like to refer to as ground level, the number underneath does the root. So in the case of a 2, that would be a square root, and if it was a 3, it'd be a cube root, and so on. And the number on the top is just a normal power. So these are the three things that we have to look at when we have these combinations going on. And sometimes we might not have a number on the bottom, sometimes we might not have a negative, but if we have them all, we have to think about all three of these pieces. So it doesn't matter what order you do it in. Now, I tend to always go for this number on the bottom first, purely because it's easier to do the root of a number than it is to then do the normal power when the number's quite large. If we imagine there was a normal power of 2 on the top, it'd be a lot easier for us to square root this than it would be to do, say, 25 squared first. So I always do the number on the bottom first. That's just personal preference, although you can do it in any order that you like. So what I've got to do here, first of all, I'm going to deal with this number on the bottom. So I'm going to go for this root first. So if I do the square root of 25, we get the answer 5. So that's the root dealt with. Now I'm going to move on to the other piece. So I've got the flip going on, or the reciprocal. So if I flip 5 over, remembering 5 is 5 over 1, if we flip that over, it becomes 1 over 5. Now the normal power there is just a 1, and a normal power of 1, let's find a different colour, I've used quite a lot now. A normal power of 1 doesn't actually change anything. Anything to the power of 1 is just itself. So that 1 over 5 there would be my final answer. Let's have a look at another one though, where that normal power on the top is something different to 1. Okay, here we go. So write down the value of 8 over 27 to the power of 2/3. So we've got 8 over 27, and our power there is 2/3. So again, no negative in this one, so we're not going to have to flip it, but we do need to deal with these two numbers. So on the bottom I have a 3, which is a root, and that is a 3 there, so that's a cube root. And on the top we have our normal power of 2, which is going to be to square the numbers. Right, so again, just like before, you can do this in whatever order you like. I'm going to stick with the root to start with, so I need to do the cube root of both these numbers. And there's a bit of a hint in the numbers in that they're both cube numbers, so the better you know your square and your cube numbers, the easier this becomes. So the cube root of 8 is 2. And the cube root of 27 is 3. So we're at 2/3 at this point. Now the next thing I'm going to have to deal with is this square. So I need to square both of them. So 2 squared and 3 squared, and 2 squared is 4, and 3 squared is 9. So my final answer there is 4 over 9. And I can leave my answer just like that. It doesn't simplify. So that is absolutely fine as a final answer. So moving on to this one. Write the square root of 80 in the form k root 5, where k is an integer. Now, the square root of 80 is a good one because there are a few square numbers that go into square root of 80. So let's have a look. 1, 4, 4 goes in. 9, 16, 25, 36. And this is where you've got to be really, really careful with surds. So we know that 4 goes in, but we do have to make sure and just check, is there a bigger square number that actually goes into 80? And it's not a very nice one to spot with the square root of 80, but 16 actually does go into 80. It goes in 5 times. So the other way that I can write the square root of 80 is I can write the square root of 16 times the square root of 5, just like we did before. And again, the square root of 16 now actually becomes the whole number 4. So it's 4 times the square root of 5. And again, just getting rid of that time sign, we can say 4 root 5. There we go, finishing off our question. Now, I think it's quite important to talk about this at this point, because if we only spotted that the 4 went in, at this point we might have written the square root of 80 as the square root of 4 times the square root of 20. And we may have gotten to the point here where we wrote 2 times the square root of 20 and then simplified down that to 2 root 20. Okay, but unfortunately at this point root 20 is not as simple, as not as small as it can actually go. So this would actually be wrong, and we'd have to continue simplifying it. I'm going to move on to another question here where we'll look at what to do in this scenario where there is a number in front of a surd that can be simplified, okay? But 4 root 5 is our final answer there. Okay, so we've got the square root of 40 plus the square root of 90. And again, I like to link this back to algebra. If we think about something in algebra like 3x add 4y, okay, hopefully we know that we can't actually add those together, we just leave it as it is. But if we have something like 3x add 4x, they can actually combine and they can make 7x. Okay, and the reason they can add together is because they have this common letter here, the x. Now we're going to take the same approach when it comes to surds. If we can have the same number here underneath the surd, underneath the square root, okay, then we can actually add them together. Now at the moment it's a 40 and a 90, so they don't add together. But let's have a look. Let's see if we can do anything and simplify this down. Let's get rid of all that. Okay. So, the square root of 40, let's have a look at that to start with. That is the square root of 4 times the square root of 10. And again, remember, just write them down, 1, 4, 9, 16, 25. We'll see if we can write enough down to start with. Right, so the square root of 40. Square root of 4 times the square root of 10. Oh, that looks like a 6. Let's get rid of that. Square root of 10. There we go. So that is 2 lots of the square root of 10, root 4 being 2, so 2 root 10. Okay, so if root 90 can also have a root 10, we can add these together. So let's have a look. Root 90 is the square root of 9 times the square root of 10. Lovely, so we've got that root 10 going on there. Lovely, the square root of 9 is 3, so it's 3 lots of root 10 or 3 root 10. Perfect, so we've got 2 lots of root 10 and another 3 lots of root 10 getting combined together, and 2 plus 3 is 5, so we have 5 lots of root 10 in total. Perfect, so we can add those together because we had that 10 underneath the square root for both of them. Okay, so writing some numbers in standard form, we're going to make this a number between 1 and 10 times 10 to the power of however many jumps we have to do in whatever particular direction. So this number here, 5,600, I'm going to hop the decimal in between the 5 and the 6. So 1, 2, 3. So that becomes 5.6 times 10 to the power of, it's a big number there, it's not a 0 point number, so 10 to the power of 3. Final answer. The next one is a small number, so we're going to have a negative power because we hop the decimal the other way this time. So 1, 2, 3 would make it 3.4. And again, this time it would be times 10 to the negative 3 because it's a 0 point number. That indicates that it's a small number. When it comes to the other way around, writing them as ordinary numbers, I like to rewrite this little bit at the start to start with. So 2 and 3, and I like to just imagine where that decimal is between the 2 and the 3. So times 10 to the power of 5 makes it a big number, so we need to hop it 5 places. 1, 2, 3, 4, 5 to the right, and then filling in all those zeros underneath. And if it is messy, just remember to rewrite that. But there's my answer, 230,000. The next one, 8.04 times 10 to the negative 3. So this is going to be a 0 point number. And again, I'm just going to write these digits out at the start, these bits here, and imagine where the decimal is at the top, 8.04. So negative 3 means it's going to be a small number, so we're going to jump it left 3. 1, 2, 3. So it's going to go there. Fill in all the zeros and tidy it up at the start. So 0.00804, final answer. Okay, so looking at this one, 4 times 10 to the 5 times 3 times 10 to the minus 2. And this is an example of one where we probably wouldn't want to write this out as ordinary numbers and work them out because it might get a little bit overcomplicated here. But let's look at applying that same little trick. So let's do the 4 times the 3, which gives us 12. And that's going to be times 10 to the power of something. I'm just going to be a little bit careful here because although we can add these powers, let's just have a look because one of them's a negative. So the powers, if I write this to the side, we're going to do 5, the first power, and we're going to add the next power, which is negative 2. And 5 plus negative 2 is 5 take away 2, so my power there is going to be 3. So that's fine, 12 times 10 to the power of 3. And again, we just need to put this in standard form because this 12 is not between 1 and 10. So instead we'll make that one jump smaller, we'll make it 1.2, and to balance that out we'll make the power one jump bigger, so 3 goes up to 4. And there's our final answer, 1.2 times 10 to the 4. Same process again. We've got 3 divided by 6 though. So let's do this to the side. 3 divided by 6, let's write that as a fraction. 3 divided by 6, if we simplify that, goes down to 1/2. So to keep this as a number rather than a fraction, I'm going to write that as 0.5. So over here we have 0.5 of 3 divided by 6. And then we've got that times 10 to the power of, and again, subtracting the powers on these. So we've got 3 take away a negative 2 on the second one, and 3 take away negative 2 turns into a plus. So we have 3 plus 2, which gives us a power of 5 for this one. So we have 0.5 times 10 to the power of 5. And again, we can balance this out because it needs to be in standard form, but this time, to make 0.5 between 1 and 10, we make it one place value bigger, to make it 5. And if we make the number bigger, the opposite this time for the power, we make the power smaller. So 5 drops down to a 4. So 5 times 10 to the 4. So a similar process, but here we had to make the number bigger, so we made the power smaller. Okay, here we go. So we've got some x squared pieces and some x pieces. Now, although all the pieces have x in, these x squared pieces we're going to treat separate to the just the x pieces on their own. So if I just have a look at the x squared pieces, we've got a 12x squared and we've got a minus 3x squared. So 12 lots of x squared, take away 3 lots of x squared, leaves us with 9 lots of x squared. And I'm just going to leave that piece separate to the x parts. So looking at the next one, we've got 5x, take away 2x, and just like we did before, 5 lots of x, take away 2 lots of x, leaves us with 3 lots of x, and that's positive 3 lots of x, so plus 3x. And there we go, we'd leave it just like that. We can't join up an x squared and an x piece, they stay separate. Okay, so expand and simplify this. Now we've got this minus 2 in the middle here, so we just need to be careful, but let's just treat it in exactly the same way. We'll times the first bracket by 3 to start with, so 3 times 2x gives us 6x, and 3 times negative 4 gives us negative 12. Now let's have a look at that second bracket. So we have a negative 2 at the start here, so we're just going to have to remember to times by negative 2. So negative 2 times x is negative 2x, and negative 2 times positive 5 gives us negative 10. Okay, so the symbol's not just getting copied there, it is getting affected by that negative 2 at the start, so be very, very careful with this negative 10 here when you're doing these. Right, so collecting it all together, we've got 6x, take away the 2x, and that leaves us with 4x's. And we've got negative 12 and negative 10 here. Negative 12 take away 10 is negative 22. And there's that expanded and simplified. Okay, so we've got another algebraic fraction here that has already been factorised on the bottom. So actually, let's have a think about how we'd approach this. Now we want to cancel off a common bracket or a common factor, and the top and the bottom both divide by x plus 2. So actually, if we imagine what this would look like if we were to sort of expand that bracket or just write it as a double bracket, we'd have x plus 2 on the top. On the bottom, it's x plus 2 and x plus 2 as a double bracket. There we go. Right, so if we cancel off one of the x plus 2's top and bottom, we're just got to be careful this time because we can cancel that one off and it will disappear. But not to forget, we are dividing by x plus 2, so when we cancel the one off the top, it doesn't just disappear, but if we divide it by x plus 2, it becomes 1. So writing our final answer, we would have 1 on the top and x plus 2 on the bottom, which again, I'll just get rid of the bracket there. So 1 over x plus 2. So just watch out with these sorts of questions here when the factor is all that there is on the top. Obviously that does become a 1 there, it doesn't just disappear. And let's have a look at one more before you have a go. Okay, so in this question we've got a slightly harder quadratic on the top and a different sort of quadratic on the bottom. So on the bottom there, hopefully you recognise that it's a difference of 2 squares. When there's no x piece in the middle there, it's because the numbers are the same and they've cancelled each other out. So if I start with the bottom, I just think it's the easier one there. The factors of 16 that are the same are 4 and 4. So our difference of 2 squares there is x plus 4 and x minus 4. There we go, and that's that factorised on the bottom. That gives us a little helpful hint for the one on the top there, which is slightly harder, because our factors of 4 are 1 and 4, or 2 and 2. Now because we've got the little hint here that we know we're going to have a 4 if it's going to simplify, we know it's going to be the 1 and the 4, but now we just need to have a look and figure out which way it goes round. So we've got 3x in one bracket and an x in another. That'll allow us to get the 3x squared. Again, obviously, check out my video on factorising these quadratics or harder quadratics if you're unsure on these. But in order to make 11 there, we're going to want the 4 to get multiplied by 3 to make 12. So we want plus 4, that'll make positive 12. And we want to take away 1, so we'll put the minus 1 over here in the other bracket. And again, now we've got it factorised, it's nice and easy for us to cancel off these x plus 4s and just write what we've got left. On the top, we've got 3x minus 1. And on the bottom, we've got x minus 4. And there we go, that is our fraction there, fully simplified. Okay, so this says simplify this fully. So we've got 8 over x plus 3, add 3 over x plus 8. Now what we need is a common denominator when we're adding fractions, just like we're adding normal fractions. So I'm going to multiply the right fraction by the left denominator. So I'm going to times the top and the bottom by x plus 3, which I'm going to write in a bracket there. It's going to help when I actually multiply it. So times the top and the bottom by x plus 3. And then I'm also going to times the left by the right denominator. So I'm going to times the left by x plus 8. And also on the top, timesing that by x plus 8, just like with normal fractions here. So if we times the top there by x plus 8, we actually get a single bracket. We get 8 lots of x plus 8. There we go. Over, and we've got a double bracket on the bottom. We've got x plus 3. That's also getting multiplied by x plus 8. And we are adding to that 3 lots of x plus 3. And on the bottom we've got that double bracket, x plus 3, x plus 8. There we go, x plus 3, x plus 8. Right, so if we go back actually expanding these numerators, and we can join it all together. So 8 times x and 8 times 8, and that gives us 8x plus 64. And on our other one, we've got 3 times x, which is 3x, and 3 times 3, which is 9. There we go. And we're going to add these fractions together. So let's rewrite these denominators in. We've got x plus 3, x plus 8. And another one, x plus 3, x plus 8. There we go, and we're adding these together. Right, so if we add them together, we've got the 8x add the 3x, which makes 11x. And we've got the 64 add the 9, which makes 53. So 11x plus 53, all over that denominator, which we can expand or we can leave it in brackets. If you do want to expand it, x times x is x squared, times 8x and 3x, so we've got 11x. And 8 times 3 is 24, so plus 24. Although you can actually leave the bottom there factorised as x plus 3, x plus 8. But we'll expand it out and leave that as our final answer there. So we have 11x plus 53 all over x squared plus 11x plus 24. Okay, so this question here, we've got quite a lot going on. We've got one fraction divided by another and it says simplify it fully. Now if we have a look what we've got to do, we know when we're dividing fractions we have to keep the first one and times it by the reciprocal, so flipping the second one over. So we can just write that out straight away if we want. I'm just going to factorise any in the process though, so I'm just going to do that to the side, well here, before we actually write anything down. So that factorises by 3, and that would leave you with x plus 2. The bottom there doesn't factorise, that'll stay as it is, so we can write this out now. So we've got 3 lots of x plus 2, all over x minus 4. We're going to times that by the flip version, but let's see if we can factorise them first. So the bottom here is quite a nice one, factorises by x, and we get x minus 4. So that's going to now be on the top when we flip it over. So we have x brackets x minus 4. And this one here, we're going to have to factorise this as well. So we've got 1 and 10, or 2 and 5. Let's have a look. Now one of them is going to be a 2x because it's 2x squared. And one's an x. Right, so let's write these down. We've got 1 and 10, or 2 and 5. And we're trying to make 9. So let's have a think. We could double the 2. There we are, that works. So double the 2, so 2 in the other bracket. Plus 2, that would make 4, and plus 5 over here, and 4 plus 5 would make 9. So we can put that on the bottom now. So we've got 2x plus 5, and x plus 2. There we go. Now if you think about what we'd have to do here with timesing fractions, if we times fractions, we just times the top times the bottom. So essentially everything there on the top is going to be on the top of our fraction, and everything on the bottoms of those two fractions are going to be everything on the bottom. So what we can do at this point, we can actually cross cancel some of these. And if you have a look, we've got an x plus 2 there and an x plus 2 here. Because obviously if we actually did multiply these together, one would be on the top, one would be on the bottom, so we can cross cancel them before doing so. So they're gone. We can also cancel this x minus 4. So that's gone as well. Obviously on the bottom there, that's the only thing there, so that will turn into a 1. And everything else has something with it. So if we times together what we've got on the top now, we've got a 3 and an x on the top of those two fractions. So 3 times x is 3x. And on the bottom there, we've got 1 multiplied by 2x plus 5. So that's just 2x plus 5. There we go. So that simplifies all the way down to that. Okay, so obviously just have a look. When you're doing one of these dividing fractions or any of these algebraic fractions, look to factorise anything you can and just follow normal fraction rules. So here we factorised everything and then timesed it by the reciprocal, flipping it over, and just cross-cancelled any common brackets there before multiplying them together, just to save us having to write it out and then cancel them off. Okay, so we've got these worded questions here, and you might recognise some of these questions as well in terms of the style that you might have seen these come up in little exams or little tests that you've done. So we've got Amy has some sweets, Bethany has twice as many sweets as Amy, and Charlie has 5 more sweets than Bethany. In total they have 55 sweets. How many sweets does Charlie have? And at first these sort of worded questions can seem a little bit confusing. It might seem that you have to just apply a bit of logic or guess some numbers, but there's a nice way that we can do this by forming and solving an equation. Now what we're going to do is we're going to allocate the letter, and we may as well use the letter x as we've been using that for the rest, but we could use any letter if we wanted. We're going to allocate the letter x to one of these people. So we have Amy, and I'm just going to write these to the side. We have Amy, we have Bethany, and we have Charlie. Now if we look at our statement here, one of these people we haven't been told anything about. So it says Amy has some sweets, it says Bethany has twice as many as Amy. So we've been told something about Bethany, she's got twice as many as Amy. And we've been told that Charlie has 5 more sweets than Bethany, so we've been told something about Charlie as well. But the person that we haven't been told anything about there is Amy. Okay, and Amy's kind of like our little odd one out there. We've not been told anything about her. So if we look at Amy, and we're going to just give her that letter, we'll call her X. Okay, we don't know how many sweets Amy has, but we know how many sweets everyone else has in relation to Amy. So if we look at that first line, it says Bethany has twice as many as Amy. So if Bethany has twice as many, she has basically double what Bethany has, so we could call Bethany 2x. Okay, and 2x just means 2 times x. Whatever Amy has, 2x would double it. So there we go, there's our expression for Bethany. Now if we look at Charlie, it says Charlie has 5 more sweets than Bethany. So Charlie has 5 more sweets, exactly 5 more than what Bethany has. Now Bethany's was 2x. So we're not going to times it by 5, it's just 5 extra sweets. So Charlie is going to be Bethany's 2x plus an extra 5. Okay, obviously if it had 5 sweets less than Bethany, we'd have 2x minus 5, but it's 5 sweets more than Bethany. So there we go, we've got 2x plus 5. Right, so we've got our 3 expressions for each person, and now we can actually have a look at forming our equation. Just as a little side note, obviously some of these descriptions could be given to you slightly differently. We could have been told that Charlie or somebody had 5 more than Amy, and then so-and-so had twice as many as that person, and that would just mean doing it in a slightly different order. For example, I mean, if it said Charlie had 5 more than Amy, then Charlie would instead be x plus 5. It might then say that Bethany had twice as many as Charlie, and I realise I'm saying quite a lot of different words here, but then we would have to double the x plus 5. So we could have these in different orders, but this is just one type of example and one type of question. So obviously what we need to do is now think about how we're going to form our equation. We've got the expressions for each person, and now it says in total they have 55 sweets. Or in other words, if we add together all these expressions, they are going to add up to 55. So if we add them all together, we've got x, 2x and 2x, that's 5x, and we've got the plus 5, so we've got 5x plus 5. And that is going to be equal to the 55 sweets. So if we write our equation then, so 5x plus 5 has to equal 55, and then we can just go ahead and solve that. So take away the 5 from both sides, we have 5x equals 50, and then we can divide by 5, and we get x equals 10. And then we can use that x equals 10 to find out how many sweets they all have, and we can just use it based on the expressions that we've got over there. We now know that Amy is x, so Amy's got 10. Bethany has double that, so Bethany's going to have 20. and Charlie has 5 more than Bethany, so Charlie will have 25. And just double checking there, they all add up to 55, and they do. So in terms of this question, how many sweets does Charlie have? Charlie has the 25 that we've got just there. Right, there we go. So that's how to go about some of these questions. And I think it's good for this question here, although we could have just substituted 10 into Charlie's expression there and done 2 times 10 plus 5, I always think it's good just to find out how many all of them have, or whatever the question's about, and then just pick the one that you need for this particular question. So as it's asked about Charlie, obviously we only need to give the 25 there as our answer. Okay, so this inequality here, we've got 6x plus 1 is greater than or equal to 2x plus 11. So obviously we've got an x on both sides here, and I'm going to treat that just like when we have equations with x's on both sides. I'm going to eliminate the smallest x from both sides to start with. So the smallest value of x is that 2x there. So I'm going to minus 2x from both sides, which is going to get rid of it on the right, and it's going to reduce this 6x on the left here. So I'm just going to write my working out. I'm just going to write minus 2x here from both sides. And let's see what we end up with. So 6x drops down to 4x. We've still got the plus 1. And that is now greater than or equal to positive 11. So I won't put the plus in. Obviously, if that was a minus there, I'd have to put that in. But there's no need for me to put plus 11 there. Now we can go about taking away the 1 from both sides. Okay, so just like on the previous question, we'll get rid of the 1. We want to get to it. So it says x is bigger than or equal to. So we're going to have 4x now is bigger than or equal to 10. And then we need to divide both sides by 4. And obviously that's going to leave us with a decimal here, because 10 doesn't actually divide by 4 perfectly. So if you have a calculator, you can type that in. But if you don't, let's have a look. Let's do this to the right here. We're going to have x is bigger than or equal to, and I'm just going to write it as a fraction, 10 divided by 4. There we go. So 10 over 4. Now, obviously, if you've got a calculator, you can just type that in. But if you don't, we just need to actually simplify that as a fraction. So if we divide the top and bottom by 2, we get 5 over 2, and that's always quite nice. 5 divided by 2 is 2.5, so we've got x is greater than or equal to 2.5, okay? Just remember, obviously, that's nice and easy to simplify. 5 over 2, 2 goes in twice with a remainder of 1, so it's 2.5 or 2.5. So that's not the nicest to draw on this number line, because it's going to be hard for me to get perfectly on 2.5, but I'm just going to do my best. I'm going to put it in the middle of 2 and 3, and this time it's greater than, so I'm going to point it to the right. Doesn't matter how long the arrow is there. And obviously, look, we've got our extra ink on the inequality there, so it can also be equal to that number. So I'm just going to colour that circle in. There we go, and that just shows that it's a greater than or equal to. The extra ink on the arrow, extra ink in the circle. And there we go, that's just obviously how we do that if we've got x on both sides. We just treat it in the same way. Hopefully you notice just by looking at it, when it says x squared minus 2x equals 15, this question here doesn't equal 0, or it doesn't equal 0 yet. So before we can actually factorise this and solve it, we need to move that 15 to the other side. That's easy enough, we just have to subtract 15 from both sides, and that will give us equals 0 on the right there. And if we do that, and I'll slot the 15 right at the end, we get x squared minus 2x minus 15 is equal to 0. There we go. And it's worth noting at this point as well, to be fair, that 2x could have been put on the other side. It could have been 15 plus 2x over here, and we had to subtract the 2x as well. Now, for the purpose of obviously this question, we're just going to have a look at obviously a nice simple one, but to be fair, we could put as many pieces as we want on the right hand side. It always needs rearranging to make it equal 0. But we'll get rid of that, obviously, because the 2x was on the left, and now we can just go about factorising it and solving it as normal. So for 15, we can have 1 and 15, or 3 and 5, and there are only options for this one, and we're trying to make negative 2 there, so we're going to have to use 3 and 5. So we'll want positive 3, take away 5, and that'll give us negative 2 in the middle there. So if we put that into a double bracket, we get x, and what do we say, positive 3, and x negative 5, or x take away 5. There we go, that's equal to 0. Always leave that equals 0 in there. Don't forget it is an equation that we're solving, so we don't just want to get rid of that. And then we can get our two solutions. I'm just going to apply the little trick this time. It's plus 3 in the bracket, so that's going to flip to negative 3, so x equals negative 3. And for the second one there, we have negative 5 in the bracket, and again if we flip the sign for that, we get x equals positive 5. And there we go, there's our two solutions. X is negative 3 and x is positive 5. And again, just very briefly, in terms of what the graph would look like there, it would go through a negative and a positive solution. I'm not going to do it to scale, but it would look something like that, that would allow it to go through a negative over here at minus 3 and a positive over here at 5. And that's all that we're actually working out. That's what we're solving, these two solutions here. I'm just thinking about what the graph would look like. So I've got a couple of questions for you to have a go at. Obviously, the main priority here is actually getting to these solutions. X is -3, X is 5. But if you want to do a little bit of an extension on top of that, you could always think about drawing the quadratic curve as well, and actually thinking about what it would look like. And I think that's a nice little extension for this topic as well. Okay, so find the equation of the tangent to the circle with equation x squared plus y squared equals 5 at the point 1, 2. Now you don't have to have a picture for this. It can sometimes just help just to visualise it, to just draw a little sketch. They're all centred at 0, 0. So we can just draw a little sketch. Doesn't matter if it's any good or not. 1, 2 will be in this quadrant here. And then we can draw part of the tangent there, and we can just label it up. So 1, 2, obviously centre 0, 0. There we go. And we can use that to try and help us visualise this. So we are going to find the gradient of this radius here, which we can do by drawing a little right angled triangle in. So the rise goes from 0 up to 2, and the run goes from 0 to 1. So we can just use that to find our gradient now. So the change in y over the change in x is 2 over 1. There we go, that's quite a nice one because that's just 2. So our perpendicular gradient, doing our negative reciprocal of 2, remembering again that 2 is just 2 over 1, so it becomes 1 over 2, and swapping to a negative. So there's our gradient. And again, from here, it's pretty much the same steps as on the previous video there. So let's just have a look. We've got y equals -1/2 x plus c, and then our coordinate is 1, 2. And if we sub that in, let's see what we get. We get 2 equals -1/2 times 1, which is just -1/2, so I won't bother writing that in, plus c. Add the half over, we get 2.5 equals c, and that's fine to leave it as a mixed number. And now we can just write our equation, just replacing c with 2.5. So y equals -1/2 x plus 2.5, and again you can write these as decimals if you want. You could write -0.5x plus 2.5. Okay, likewise you could even write 2.5 as 5 over 2. You can leave it as a top heavy fraction if you want, or any proper fraction. Absolutely fine for you to do. As you can see, that one there was a little bit nicer than the last one. Okay, so just showing you that they're not all that nasty. Still obviously a difficult topic, but that's a nicer version of one of these questions. Okay, so our first question, we are starting with a quadratic. Now we know that a graph is a quadratic if it has a little squared in it. So this particular graph has x squared, and this is quite a nice one. It's just x squared take away 4. Now normally you're asked to complete a table and then also draw the graph. Now my main priority for this video is going to be on actually getting these tables completed. I like to hope that we can all draw these graphs once we've got the coordinates. So I'm not going to stress too much about the actual drawing here. In fact, the actual graphs that I've got on the screen are quite small and mine aren't going to be perfect, but I'm just going to give you the general idea of how to go about drawing all these graphs here. So for this one here, we've got y is equal to x squared take away 4. Now that obviously means just to find the y coordinate, we square the x coordinate and then take away 4. So it's hopefully quite nice and simple. We're going to have a look at a trickier one after this, where you've just got to be careful with how you actually go about doing this. So it says, for all the values of x from -3 to 3. Now if it doesn't give you that information, you can find them along the x-axis here. If you have a look, the x values stretch along from -3 along to 3 there. So that's where we get them if it doesn't tell us, okay, or if we're not given a table. But for all of these, I am going to give you a table. Now obviously we are starting with this one on the left, so we've got -3 there, and we need to sub that into our equation. So to find y, I'm just going to write the working out. We would do x squared, so -3 squared, and we've got to be very careful when we're writing -3 squared, because particularly if this is a calculator question, if you type that into the calculator, you are going to get the answer -9, because what the calculator does is it squares the 3 and then puts the minus with it. It doesn't actually do -3 squared. So a really important little thing that you need to remember throughout this is that we're just going to put all our numbers in brackets like that. Okay, so we're going to write -3 in brackets squared, and then we're going to take away 4. Of course, if this is non-calculator, we can work that out anyway, because we can do -3 squared, which is +9. So we've got 9 take away 4. And that gives us the answer 5. So we know that that number there is going to be 5. We can then move on to the 0. And again, I'm not going to write all the working out down for every single one here, but we would just do 0 squared. Again, we'll put the 0 in brackets, although it doesn't matter if the number's not negative, and then take away 4. And 0 squared take away 4 is minus 4. So we can just put minus 4 straight in there, and the rest, and this next one here I'm going to do without writing the working out down. We've got 1 squared, which is 1, take away 4, which is negative 3. Now it's not that easy to spot, but obviously when it comes to straight line equations, there's always quite a nice pattern in the table. When it comes to quadratics, they're not the nicest of patterns, okay, and the others aren't going to follow a pattern, but there is actually a bit of a pattern in a quadratic. If you have a look, we've got minus 4 in the middle, and either side of that we've got negative 3, either side of that we've got 0, and either side of them we've got 5. So there is a bit of a pattern, although I certainly wouldn't rely on these because they don't stay there throughout all of the graphs, and sometimes it's very difficult to spot some of these patterns. But just thinking about the fact that there is a bit of a pattern when we're looking at these. So let's have a look then. Actually plotting this on the graph, now we've got an x and a y coordinate there, that little bit there, x is negative 3, y is 5, so that's the coordinate minus 3, 5. Now I'm going to plot these quite quickly. Minus 3, 5 is somewhere up here. I'm not going to be able to do them perfectly on the screen here. Then we've got negative 2, 0. We've got negative 1 to negative 3, obviously getting your x and y coordinates the right way around here. 0 to negative 4, and then it repeats the pattern going up the other side there. So we've got 1 and negative 3, we've got 2 and 0, and we've got 3 and 5, which is somewhere up there. Right, so in terms of actually drawing the graph here, we've plotted the points. We now need to get a nice smooth curve that goes through all of the points. So not with a ruler, a nice smooth curve, and it has to go through every single point. So I doubt I'm going to get this perfect. I'm going to give it my best shot. I'm just going to do a nice smooth curve. Ooh, no little kinks in it. I actually can't see them as I'm doing them. There we go. So I've done it as best as I can, but you want to get yours nice and smooth. Okay, so make sure you do it with a pencil, rub it out if you have any kinks like I've got down the bottom there, but then you can go back and have a go and actually rub it out and just make sure you get a nice smooth curve there. Right, so that's what a quadratic graph looks like. We're going to have a look at a slightly harder one. Before we move on there are a couple of things to know about this quadratic graph and a couple of the points that are important. We're not going to look at them specifically in this video, but there are 2 places which are, well, technically 3, but there are 2 things that are quite important with a quadratic graph. One of them is this point right here at the bottom where it sort of stops going down and starts going up. That can be called a couple of different things. It's got a specific coordinate there. It's 0, minus 4. It can be called the turning point. There we go. Or it could be called the minimum point or the maximum point if it's sloping another way. So the minimum point or turning point. There we go, the turning or the minimum point, that's a very key place on a quadratic graph. And there's also 2 other points here, which is where it crosses the x-axis. So we've got these 2 points there, which is negative 2 and 2. Let's just write that in there, minus 2 and 2. And these have a special name as well. They've got 2 names again. They can be called the roots. There we go. Or they can be called the solutions. There we go. Roots or solutions. So we're not going to focus on those points in this particular video, but obviously just a couple of extra little bits to be thinking about there. The roots and the solutions where it crosses through the x-axis, and the turning or minimum point down the bottom. Obviously just adding a little bit of context to the language there. The turning or the minimum point seems like quite an obvious place, so you would just give that as a coordinate 0, 4. But then the roots, okay, doesn't always necessarily have a bit of a logic there, but I do like to think of this x-axis as being ground level. And when you think about plants and things like that, where they meet the ground is where the root starts. So I do like to think of these sort of things as like the little roots there, and that's sort of where the word comes from. But you've also got the word solutions, so there's not really any context there, but it's just where it meets the x-axis there. Okay, so what we're going to have a look at is some equations of lines where it isn't in the form y equals mx plus c. So whenever we're looking at lines, we need it to be in this form here. Now it can be written in other forms, we can use them perfectly fine, but in order to compare them and in order to find out the gradient, it needs to be in this form here. So looking at this question, it says, here are the equations of 4 straight lines. 2 of the lines are perpendicular, which 2? Now if we look at this first one, it's not in the form y equals mx plus c. Okay, it has a 2 in front of the y, so in order to get it into the form y equals mx plus c, we're going to have to divide everything by 2. Okay, so I'm just going to write divide by 2. I'm going to divide both sides by 2. So 2y divided by 2 gives us 1y. We've got 1x there. 1 divided by 2 is a half, so that 1x would become a half x. And the 1 divided by 2 at the end would become a half, so that's plus a half. There you go, half x plus a half. So there's my first one. Let's have a look at the next one. Now this doesn't have anything in front of the y, but it does need rearranging. Look, the x there is on the left hand side of the equal sign. So if we add or plus 2x to both sides, we would get y equals, and just to keep it so that the x part's here, although I don't have to, I'm going to stick it in front of the 4. So y equals positive 2x, so as it's in front of the 4, I don't have to put the plus sign. But there we go, we get 2x, and then we do have to introduce the plus sign for the 4 there, so plus 4 as it is positive 4. There we go, 2x plus 4, and that's my second one. So look at the third one, what we're going to do for this one. Okay, so we've got a 3 in front of the y, so we need to divide everything by 3 so that it says y equals. Don't have to rearrange it at all, but dividing everything by 3. So dividing that by 3, we get y equals, 6 divided by 3 is 2, so 2x, so 6x divided by 3 is 2x, and then add 5, and 5 divided by 3, let's leave that as a fraction, 5 over 3. That just means 5 divided by 3 there, rather than trying to actually work that out. So 5 over 3 is fine, as we are also looking at the gradients here to decide which two are perpendicular, because that's what we're trying to have a look at, which ones are perpendicular. We don't really need to worry about the y-intercept there, okay? But there we go, let's have a look at this last one. Okay, so nothing in front of the y, but the 2x is in the way here, so we need to minus 2x from both sides to get that out of the way. And again, just like before, I'm going to put it in front of the 3. So y equals, we're subtracting 2x, so minus 2x. There we go, and then that is positive 3 again, so plus 3. Right, so we need to have a look at which ones of these are perpendicular. Now, as we've got, and let's see if we can highlight this, we've got a 2x and a 2x here. So those two lines there are parallel. Not asking for which ones are parallel, but they have the same gradient, so we could say that those two are parallel. So let's have a look at the other two. So we've got these two here. So the gradient of the one at the top, so the gradient of A is a half, and the gradient of D down the bottom there is negative 2. And if we think about this, how do if half is my gradient, my negative reciprocal would be negative 2, wouldn't it? You'd flip it over, it'd be negative 2 over 1, which is negative 2. So therefore those two lines must be perpendicular, okay? So it's just something to be thinking about in terms of different line equations, what they can look like and the way we want to have them. We want to have them as y equals, we don't want any numbers in front of the y. If we do, we're going to divide it. And if there's anything next to the y, we just want to move it over to the other side, okay? But they're A and D there are my two lines that are perpendicular. But we're going to be having a look at some line equations next, where they might not necessarily already be in the form y equals mx plus c, and that just hints to you that you do have to change them first. Okay, so this question says, Carol runs a race. The graph shows her speed in meters per second, t seconds after the start of the race. Calculate an estimate for the gradient at t equals 4 and explain what your answer represents. And obviously this type of question, we already know now what the answer represents. If we find where t equals 4, which is just here, there we go, we obviously know that once we work out that gradient, that is going to show her acceleration. So let's just write that in straight away, that shows her acceleration. Right, there we go. So let's work out the acceleration at that point, or the gradient at that point. So t equals 4, again, this is not the nicest for me to draw here, but I'm going to do it as best as I can. Right, there we go. To be honest, actually looking at that, I'm not going to keep drawing this over and over again, but I'm not actually very happy with the fact that there's quite a big gap here, and there's not really much of a gap on the right hand side there. So to be honest, if I had this on paper right now with a ruler and a pencil, I'd be rubbing that out and doing it again. But as we're just running through the process here and having a little practice, I'm going to leave it as it is. I'm just going to go ahead with it and see what we get. But obviously, if you are following along with me on the paper with this, obviously try and make yours a little bit more accurate than mine there. Now it looks like I've got quite a nice triangle that I can draw in. I'm going to go across from here to here, and again you can do this however you like. You can make it whatever size you like, you just need to read accurately. But I've just gone along from 3 to 6 there, and I'm going to go up, and I look like I get some quite nice numbers here, so I'm going to stick with this. Now the run there goes from 3, which is just here where the start of that orange line is, along to 6, so that is a run of 3. And it goes at a height from 7 up to 10. If anything, maybe it's just over 10, but 7 to 10, there we go, that gives me a height of 3 as well. There we go. So in this case, I've got a rise over run, or a change in y over change in x. I've got 3 divided by 3, 3 over 3, and that gives me an answer of 1. There you go, meter per second squared. Right, there we go. So there is an answer for this one here. Now I'm just going to do that one more time. I'm going to do this quite quick. I'm going to see if I get the same answer. There we go, because obviously I don't think it was super accurate, so I'm going to have one more go. So let's have another look. Okay, let's just draw as best I can. That is even worse than the last one. Let's have a go at one more time. Okay, maybe one more. There we go, I'm a lot more happy with that one. Let's see if this works. Very difficult to do without a ruler, but there we go. Let's have a look. So let's go across. I'm going to make it a little bit smaller, my triangle this time. I'm going to go from here to here, and then I'm going to go up. There we go. So my run there goes from 4 to 6, so that is a run of 2. And my rise there goes from 8 to 10.2 by the looks of it, so that is a rise of 2.2. Right, there we go. So in that, for that working out there, for the second time I've done it, my rise is 2.2, my run is 2, so 2.2 divided by 2 gives me 1.1 meters per second squared. And there we go. So we've got a slightly different answer there, so you can see how obviously just changing the gradient slightly is going to slightly change your answer. But these sorts of exam questions, you are going to have an allowed amount of range there, so it's going to be somewhere between 1 and 1.2 or something like that. Okay, but obviously you just want to do this as best as you can. Make sure you show you're working out, make sure you draw your tangent in nice and clear, make sure you show where you've got your numbers, make sure you show your rise over run, write down change in y over change in x, show those numbers. Okay, and then even if your tangent isn't great, you're not going to lose more than 1 mark on a question like this. But obviously just a little bit of practice getting those tangents perfect. Okay, so here's quite a different question. It says the diagram shows a pattern made by 2 regular polygons. Work out how many sides tile A has. And what's not very nice about this one is it doesn't show you all of the sides here. Obviously that's why it's asking us how many sides it has. It just shows us part of tile A, and then we've got the equilateral triangle there. So have a go at this one, see if you can work it out. I'm going to go over the answer, but see what you get. See if you can figure out how to apply some of the methods we went over in that first slide there, and see if you can get the answer. So pause the video, have a go, and we'll go over the answer in a sec. Okay, so looking at this question then. Now first things first, let's have a look at the angles around this point right here. Now we know in the equilateral triangle, that's an angle of 60 degrees. And if tile A is the same on both sides, then what we can do is take that 60 away from 360 and split it in half. So if we do that, so 360, take away the 60 degrees in the triangle, leaves us with 300. And if we divide that by 2, we've got 150 degrees in each of these tile A's here. So 150 degrees and 150 degrees. So what the question's now asking us is what polygon, or how many sides does a polygon have to have that interior angle of 150 degrees when it's a regular polygon? So 2 different ways we could do this. Now we could just guess. I could just say, okay, well let's just guess 14 sides. And then if it is 14 sides, I'll take away 2, times it by 180, divide by 14 and see if it matches. And if it's too high, I'll go lower, and if it's too low, I'll just go higher with my sides. Okay, but we can take a little bit of an easier approach here. Now if you remember on that first one, when we looked at the polygon, if it had an interior angle of 150, we could have a look at what the exterior angle is. And because it's on a straight line, the exterior angle would be 30 degrees. So if you think about this, if you remember that all the exterior angles add up to 360, well if one of them's 30, obviously 150 and 30 make 180, then I could just say, alright, well, if I do my 360 and I divide it by the exterior angle there, which is 30, that gives me a total of 12. There we go. And that tells me that there must be 12 angles around the polygon, because obviously that 30 fits in 12 times. So there we go. Working that out then, we've got 12 sides as our final answer. And again, you can check that. If I was to do 12 take away 2, that would be 10 times 180, and then divide it by 12 and you get the answer 150. So you can always check that out. Okay, so this question here is not a right angled triangle. It is a type of triangle, though. It's an isosceles, and that is shown to you via these 2 lines here, drawn on those 2 lengths. Obviously, if we had another one on the bottom, it would be an equilateral, but you can already see it's not an equilateral as the side lengths are different. But this is an isosceles triangle, meaning both of those diagonal lengths there are both 17, matching this one just here. Now again, with a triangle like this, we are just going to use the same formula, and that is that the area is equal to half base times height. There we go, which again you could write in a different way if you prefer. You can write down base times height, or BH, divided by 2. So for this one here then, we just need to identify the base and the height. The base is 16, and as you can see, the height is 15. So for this particular one, we're going to need to do 16 times 15, and again ignoring that diagonal length. So if we write that down, we've got to do 15 times 16. Now obviously that's probably not one that you're going to do in your head, but you could obviously just write your working out to the side. Now the answer for that comes out as 240, and we need to actually halve that. So 240, if we divide that by 2, gives us an area of 120. And again, we would write that with centimetres squared, so it's 120 centimetres squared. Now, particularly when you've got larger numbers like this, you could save some time by using the first formula, and that is to halve the base before you multiply it by the height. So instead of doing 15 times 16 and dividing by 2, we could have just halved the 16 and done 8 times 15 instead, and that as well would give us 120 straight away, and we wouldn't need to halve the answer. So up to you which method you use, either one is fine, but that is how you work out the area of a triangle. You do the base times the height and divide it by 2, or you just do half times the base and then times that by the height. Okay, so when we're looking at the area of a sector, and particularly when we're doing it in terms of pi, some of these questions can be easier, sometimes they can be slightly harder, but this one is sort of in the middle. So it says here that the diagram shows a sector of a circle radius 7. Work out the area of the sector and give your answer in terms of pi. So all we're going to do is do the working out as we would when we were using a calculator, but we're just not going to actually type it in. So to start with, we need to know our area formula. So the area of a circle is pi r squared. When we are looking at a sector, we also multiply it by the fraction that we're looking at, which I'll call theta over 360. So in this case, the angle is 40 degrees and the radius is 7. So if we plug that into our formula there, we have pi multiplied by 7 squared multiplied by 40 over 360. Now we obviously want to simplify this a little bit so we can get a bit of a simpler answer that we can give in terms of pi. The first thing that I'd probably simplify is the 7 squared. So that's going to be pi times 49, which you can write as 49 pi. And then we're going to multiply that by this fraction. I want to simplify that as well. So if I do that to the side, 40 over 360, for starters you could divide them both by 10, which would give you 4 over 36. Then of course both divide by 4, so that would become 1 over 9. So we're going to times that by 1 over 9. Now the easiest way to go about this is to just simplify those numbers. So 49 times the 9th just means 49 divided by 9. Now that doesn't actually simplify, it doesn't divide perfectly, so that would just be the fraction 49 over 9. So I'd just say that this is 49 over 9 and put the pi symbol after it, and that would be my answer there in terms of pi. Of course, if they did divide, you could simplify that fraction further, giving it as a whole number, but of course as it doesn't and we're writing it in terms of pi, it's fine for us to leave it just as it is in a fraction. Let's work out the total surface area of the cuboid. Now when it comes to a cuboid and we're working out the surface area, we need to remember we are going to work out the area of each individual surface. And when it comes to some of these shapes, you can't always see each of those surfaces. Now if we think about what we can see that we have the face on the front. And the same face that's on the front, which I've labelled number 1, is also on the back. So we're going to have 2 of those rectangles there for those 2 surfaces. If we also think about what else we also have the shape here on the right, which is another rectangle. And that is also going to be on the left-hand side of the cuboid as well, even though we can't see that one. And for the final shape that we have the rectangle that's shown on the top, and that is face number 3, and that is the same as the face on the bottom. So when it comes to a cuboid, we actually have 2 of each face. And when it comes to a cuboid, we also need to know how to work out the area of a rectangle, as all of these faces are just rectangles. So when we're looking at each one, we just need to identify the side lengths for each individual rectangle, work out their areas, and then we'll combine them all at the end. So if we start with face number 1, if we have a look, the width and length in either order is 8 and 10. So to work out that area, we would just do 8 times 10, and that would give us an area of 80, and we will worry about the units at the very end. Now again, that is the same as number 1, so number 1 is also 80, so we can label that for both of them. We're going to then move on to another rectangle, and as I've already labelled it, number 2, we'll start with that green one. So if we look at that one there, the length of that rectangle down the bottom is 5. Now the actual width or the height of this cuboid we can get from the other side, and that is a height of 8. So we have a height of 8 centimetres. So to work out that area there, we would do 5 times 8. So just make sure that you get those lengths from wherever you need them. So if I write that down, that is going to be 8 times 5, which is going to be 40. And that is another one of our areas. Again, we can label that with our other side, which is also 40. And on to our final one, we've got the rectangle on the top and the bottom. Now again, we're going to have to label both of these, but if we look at the top, we have the area, and let's just get rid of that. We've got 5 down the bottom, and the other area, the other length is 10 just down here. So if we label that up near our rectangle, this is 10, and this is 5. So to work out the area of number 3, we would do 5 times 10, and that is equal to 50. And again, that is the same as the one down the bottom, which is also 50. So again, you might have noticed that in all of these multiplications that we've done to work out in each individual area, each one has a different pair of numbers because all of the lengths on the cuboid were different numbers. So for the middle one there, the front face, we had 8 times 10. For the side, we had 8 times 5. And then for the top, we had 5 times 10. So it's up to you in terms of which process that you do. When it comes to a cuboid, what you can do is just work out the area of each individual face, the 3 that we worked out. You can add them all together and then double your answer. Or you can obviously work out all of the individual faces, even though they're matching pairs, and then add them all together. So completely up to you, but if we go ahead and add them together now, we have 80 and 80. We then also have our green face that we worked out, which is 40 and 40, and then our final 2, we have 50 and 50. And all we need to do is add all of those together, so let's add them all up. So we've got 80 plus 80, which is 160, plus 40 gets us to 200, plus the other 40 gets us to 240, and then we've got an extra 100 there, which is 340 in total. And now we want to give our units, it was in centimetres, and we're looking at an area, so it's centimetres squared. So our final answer for this question would be 340 centimetres squared. Now when it comes to a cuboid and we're working out the volume, what a lot of people will do is they'll just multiply all the sides together. And that is absolutely fine, that will work, but it doesn't really help with the understanding of how to move through all the different shapes. So what's important to note is that when we work out the volume of a shape, we work out the area of what's called the cross section, and then we multiply it by the depth or however far that goes through the shape. And in regards to a cuboid, the cross section can actually be any of the faces. Now all that the cross section is, it's just one of the faces that goes or extends all the way through the shape. Now in regards to the cuboid here, as it's the one facing us, I'm going to look at this one as the cross section. And if you kind of imagine slicing it, if it was, you know, something that you were able to slice down the middle, that cross section would stay constant all the way through the shape here going in this direction, which in this case will be the depth. But as I said, when it comes to a cuboid, to be fair, you could actually look at any of the faces as the cross section. Take the right hand side, for example, this one here. We could actually slice it down that way, and that face would also go through the shape in this direction if I can try and draw that in. Okay, but as it stands, I'm just going to have a look at the front face there, and we're going to use that as the cross section. Now as that is a square, sometimes most of the time that's going to be a rectangle, but in this particular one here, they're both 20. To work out the area of that cross section right there, when it's a rectangle or a square, we just do the length times the width. So the first thing we work out is 20 times 20, which is 400. Obviously that's an area there, so our units would be centimetres squared, but we're not going to worry about the units until the final step here when we work out the volume. Now the next part of that process is obviously to multiply that by the depth, and in this case the depth, how far it goes back, this distance here, is 40 centimetres. So all we're going to do to finish this off, to get our volume, is we're going to take the 400, the area of the cross section, and multiply it by the depth, which in this case is 40, and that gives us 16,000, and that will be centimetres cubed. Okay, not forgetting that when we have volume, our units there are going to be cubed. Or potentially when we're looking at liquids, we might have something like litres or millilitres. So that is how you work out the volume of a cuboid. Okay, so this question says a rectangular frame is made from 5 straight pieces of metal. Work out the total length of the metal needed. Now in order to do this, you can obviously see that the rectangle around the outside, we have 12 on the bottom and 5 on this side. So they're going to be matched up on the other sides. This will be 5 and this will be 12. We just need to find that diagonal length. Now obviously that means we're going to have to use Pythagoras, as we're finding a missing length in a right angled triangle, and we've got the other 2 lengths. And obviously Pythagoras can appear in lots of different formats. This is quite a nice one though, so if we find this, we can do, and we're finding the longest length, so we're going to square the sides and add them together. So we've got 5 squared, add 12 squared, and that is 25 plus 144, which is a total of 169. Now when you are doing Pythagoras, regardless of whether you're finding the longest side or the shortest side, you want to square root your answer. And if we square root 169, it's not one of the most commonly known ones to be done without a calculator, but the square root of 169 is 13. So that's going to come out as 13, and of course we're looking at metres with this particular question. So that's going to be 13 metres, and of course this was 5 and 12. So now all we actually have to do is add them together. Up to you how you add them. I'm going to add the two 12s to start with, which is a total of 24. Then I'm going to add the two 5s, which is a total of 10, just to make it a bit quicker to do the addition. And then we're going to add the 13 into that and just add them all up. So 4 and 3 is 7, and then 2, 3, 4. So we get 47 metres in total, and that'll be the total length needed to make this particular frame. So there we go, a little bit of Pythagoras involved in a slightly different type of question. Okay, so find the exact value of tan 30 times sine 60 and give your answer in its simplest form. Now if you had a question like this, obviously we'd have to start drawing out our triangles and work out what tan 30 and sine 60 is. Quite a nice one because you only have to use the one triangle for 30 and 60, and if you can remember some of them, you actually can just get away with doing half of the triangle, which is what I'm going to do. And we've got 2, 1 and root 3. And again, we just need to read these values. So I'd be writing down SOHCAHTOA again, just to make sure that you know which ones you're reading. SOHCAHTOA, there we go. And let's just get these two values from the triangle. So tan 30 is opposite over adjacent. So we're looking at the 30. Opposite the 30 is 1 and adjacent is root 3. So tan 30 is 1 over root 3. There we go, and there's your first one. And the next one is sine 60. So moving on to the sine 60, looking at the 60 angle, opposite over hypotenuse. Opposite is root 3, hypotenuse is 2, so it's root 3 over 2. There we go, and it asks us to multiply these together. So what we've got to do is multiply them together and see what we get. So on the top, 1 times root 3 is root 3, and root 3 times 2 is 2 lots of root 3. So 2 root 3, there we go, and that is finding the exact value there. It does say though, give your answer in its simplest form, and that's because of the top and bottom here divides by root 3. So we can divide the top by root 3, and we can divide the bottom by root 3, and that'll simplify the fraction, just like a normal fraction. So root 3 divided by root 3 is 1, and 2 root 3 divided by root 3 is 2. So our final answer there would be 1/2. Okay. There we go. So it's quite nice and quick to find them once you know those triangles. I think it's quite a nice visual way of actually just being able to find them quite quickly. But you have got to actually know how to draw those triangles and understand where these values actually come from. Okay, so looking at this question, it says B is the midpoint of AC. That's this one here. So it says that this is a midpoint. Now straight away, if you have a look on that line, look, A to B is the vector A, and if that's the midpoint of B to C, then this here on the other side has to be exactly the same, so we can label that A straight away. So that's another A. It says M is the midpoint of PB. Let's find that. That's here. M is the midpoint of PB. And if it's the midpoint, it's not in a ratio this time, but a midpoint means it's in the ratio 1 to 1, or 1/2, and the half here. And just also taking note of that line there, BP, you can see doesn't have any vectors on. Every other line has a vector on, but B to P or P to B, whichever way we look at it, has no vector on it. So that line there is going to be one that we're going to have to find how to move up and down. It says show that NMC is a straight line. So if I draw that in, let's have a look. NMC, quite hard here without a ruler, but NMC, there we go. That's the line there we're trying to prove is a straight line. Now when it comes to these types of questions where you've got to show it's a straight line, we just need to have a look at this green line here. So there's 3 vectors I can have a look at on this green line. I can go right from the start, from N, all the way up to C. That's a vector I can have a look at, N to C. Or I could do part of the line. I could go from N just to M. That wouldn't get me part way along the line, so I've got N to M. Or I could go from M, that line there with the cross on, up to C. So 3 possible vectors there that we could have a look at. Now when we're trying to prove something's a straight line, I only have to find 2 of these, and it tends to be that this one here is the easiest to find, the full length of the line, and I always look for that one first. Then I just pick and choose between one of the other 2. And you're going to see we're going to be able to prove something's a straight line because there's going to be something that is similar within the vectors there when we actually find them. Okay, but we'll go about actually just trying to work them out first, and then we'll see at the end how it proves it's a straight line. But N to C, that's quite a nice easy one actually, because I can go from N here, I can go backwards up this 2b. So I'm going to write this down, the vector N to C. So I can go minus 2b. Let's have a look, minus 2b. because I'm going backwards through that 2b. And then I can move all the way down the line here from A to C, and that's 2 of those a's there, so plus 2a. There we go, and there's the vector n to c. And I'm just going to rub these lines out, let's get rid of those. Okay, so that's my vector there, and again I can rewrite that if I want to get rid of the symbols. I can write 2a minus 2b. Okay, so now we have the vector 2a minus b. That is from n to c. Now, that's one of our vectors done. So, let's tick that off, one of the 3. Next, let's have a look at one of the other ones. It doesn't really matter which one we pick, n to m or m to c, it doesn't really matter. Let's just go for the second one, as it's the second one that I wrote. And we just need to think how we're going to get from n to m there. Okay, so we have 2 options. Either we could go down here, and then up there, or we could go from n to a to b, and b down to m, all the way around. Now that's 3 parts there, so I'm just going to ignore that one. I'm just going to go down and up. Okay, so to get from n to p, that's okay. That's just down this little vector b here. But then I have to work out how to get from p to m. Now, in order to get from p to m, okay, this part here, I need to be able to move up the full length of the line. So I need to know what the full vector there for that line is, and that line is the vector p up to b. So I need to work out p to b now. So let's have a look at how we could go about getting p to b. Okay, and then we'll think about adding all these up together in a sec. So to get from p to b, let's write this one down. And we'll write that down over here, p to b. I have to go up here to a, and then from a over here to b. So to get from p to a, let's have a look, we have to go backwards through this b, and backwards through another 2 b's. So that's going to be minus 3 b's, so minus 3b. And then plus this a up here, so plus a, so minus 3b plus a. Okay, now that gets me from p to b. Now we don't want to know p to b, do we? We want to know how to get from p to m, which is going to be half of that. Okay, so to get from p to m, I'm going to have to halve that. There we go, because m is the midpoint, we only want to go halfway up that line, half of that vector. So we just need to do what we did before. We'll stick a half outside the bracket. I'm not going to rearrange it here to make it a minus 3b. I'm just going to do it as we've done it here. So minus 3b plus a, and we're going to do half of that. Okay, so if we expand that, let's have a look. A half times minus 3. Remember, you can always think of these as fractions over 1. So a half times minus 3 is minus 3 over 2. So minus 3 over 2b plus, and a half times 1a is a half a. So plus 1/2 a. There we go. And that's our vector p to m. Now we're almost done, because if we can get from n to p, which we can, we just go down a b. Now we can get from p to m using this vector here, minus 3b plus half a. So if we have a look at this one here, let's label this up. So we're now going from n to m, the full bit there. And in order to do that, we do 1b, so b, and then add to that this vector here that we've just worked out. Okay, so we're going to bring that down here. Okay, literally the one we've just worked out. So b, and I'm going to put the half a next to it. Let's have a look. In fact, no, let's put the minus 3. So it's not going to be plus, because it's minus 3.5b. So we could put add minus 3.5b, but I'm just going to get rid of the plus and just put it in there just to avoid having extra symbols here. So it's b minus 3.5b plus a half a. There we go. Right, so again, we just need to simplify this down. We're almost done. We just need to simplify this. And if we have a think, let's have a think. The b's there in terms of halves. So 1b is 2 halves b. And 2 halves b, take away 3 halves b, is going to leave us with minus a half b. Okay, 1 take away 1.5 is minus a half. So if we work that out, we've got minus a half b plus a half a, that half a that we've got there. And that's our final vector there to match that up. Now, that means we've done n to m, so we can tick that off. Okay, now we've got 2, we just need to have a look and see if we can compare these. Now, I mentioned in the last question, it's very, very important here that we factorise these vectors and we can see if there is anything common between them. We'll have a look. So if I come back to this n to c one, the first one, if I factorise this one here, and rather than rearranging it, I'll factorise this one, I could take 2 out. And if I take 2 out, that would leave me with minus b plus a inside the bracket. Okay, and that there is going to be a really key vector, so I'm going to highlight that. 2 lots of minus b plus a. If I do the same again to this one, so if we factorise this one as well, just see that was that one factorised. If we factorise this one, the only thing we can factorise out is a half, so I could take a half out. Let's have a look. So take out a half, divide the first bit by a half, we get minus b. A half divided by a half is 1, so minus 1b. And then dividing a by a half, we get plus a. There we go. And that's that vector there if we factorise it. And again, I'm going to highlight that one. And let's just write them down over here next to these vectors that I was going to work out in the first place. So for n to c, we have two lots of minus b plus a. And for n to m, the other one we worked out, we've got a half brackets minus b plus a. There we go. So if you have a look, we've obviously got this similar bracket. We've got this same vector in there, minus b plus a. Now, if we've got the same vector there, minus b plus a, it means that the lines are going in the same direction. And if they're going in the same direction and they're connected here at m, then they must be on the same straight line, because if they're going in the same direction, they're connected together at that point m, then they have to be going in the same straight line. The 2 there in n to c means that's the full length of that, so it's doing 2 lots of that vector. The half means that from n to m is half of that vector, which means if we had have worked out this line here, m to c, it would have been the other 3 halves, or the other 1.5 of that vector. Okay, so you'd get 3 halves of minus b plus a. And you could work that one out as well, but we only ever have to work 2 out. Now, that is enough to show that it's a straight line, but personally, particularly if it ever says prove or anything like that, I'd just like to write that they both share the same vector. You can say that they share different multiples of the vector. One's 2 lots of it, one's half lots of it, but I would normally put a little statement in, just pointing an arrow at those brackets and saying that they share the same vector. Okay, so obviously that is quite a tricky one. It's not some of the hardest of the vectors. Some of these new vectors seem to be very, very tough, but there's a lot going on in that question there and a lot to be thinking about. Okay, so this one says work out 12.5% of 160. So again, we'll work out 10%. So we get our 10% here is going to be 16 when we divide it by 10. Again, we'll halve it for 5%, so that gives us 8. And again, halving that for 2.5% would give us a value of 4. So how do we get to 12.5%? Well, 12.5%, we could use the 10% and then the additional 2.5%, and that would give us our 12.5%. So again, for this one, we just need the 16 and the 4. We just have to add those two together. That gives us an answer of 20, and there we go, final answer. Right, so as you can see, these ones aren't actually too bad. In order to get a 2.5%, you just have to find your 10%, halve it for 5%, and then halve it again for 2.5%, and then just carefully think about your combinations that you're going to put together in order to get to that final answer. So it says Alice and James share £80 in the ratio 3:2. Work out how much they each receive. Now, first things first, whenever I'm looking at a ratio, I always bring it away from the words. So rather than looking at these words here, I'm going to have A and J as my Alice and James. I'm just going to bring that away from all the words there. And it says that they share it in the ratio 3:2. And obviously not forgetting, when it comes to ratios, that first name that's mentioned is correlated or relevant to that first number that's mentioned there. So when we obviously have a look at this, we've also got James, and James is going to be the 2. So we can pair those up and bring it all away from the words, and it says that they share £80 between them. Now, when we're looking at the ratio here, that is relating to both these numbers here. So both these people are going to share £80. Now, you can do this obviously just numerically, or you can actually draw a little picture. But essentially, when it comes to a ratio, that we just need to think about how many parts that number is referring to. So obviously, we've got £80 as our number, and that is referring to the total amount of money that they both share. And they both share, look, 3 and 2, and that makes 5 parts. There we go. So they've got 5 parts between them, and that equals £80. So when it comes to any sort of ratio question, we want to know what the value of 1 part is. So if we've got 5 parts that equal £80, we can get the value of 1 part by dividing by 5. So we get the value here of 1 part. There we go, and 1 part therefore is going to equal 80 divided by 5, which is £16. There we go. So 1 part of this money, of this amount that's being shared in this ratio, is worth £16. Now obviously we've got Alice that's getting 3 of those parts. So Alice is getting 3. So Alice is going to get 3 times the 16, which is £48. There we go. And James is getting 2 of them. And James's share then is 2 lots of 16, which equals £32. There we go. And you can always do a little quick check at the end there, because those two numbers should add together to make the original 80, and 48 plus 32 adds together to make 80. Now, if you're not really the most fond of just doing it via the numbers, you can actually take a different approach to some of these. I won't do it very often because it does actually sort of just create a little bit more work for yourself. But if you don't like doing it as the numbers, you could have a think about what this actually looks like in terms of a picture. And I might talk about this a little bit, but if Alice is getting 3, if we imagine she's got 3 little piles of money there, and James has got 2, there we go. We know that that £80's got to be split between those 5 piles, so we can do 80 divided by 5. It's a very similar process, gives us 16. And then you can just fill in each of those little piles of money with 16s. There we go. And then obviously just count them up there. So Alice is getting the 3 of them, and those 3 are worth 48. And James is getting the 2, and that's worth 32. So you could rewrite it as a ratio, 48 to 32. Obviously it's about money, so it would include the pound sign there. But there we go. Now, a lot of these questions that I'm going to focus on to start with, I am just going to be looking at money, but these questions can be to do with anything. It could be recipes in an ingredients in a recipe, sorry, or it could be something like, there's quite a lot of questions where it says they're sharing sweets or sharing that, something out. Whatever that may be, we're going to take the same approach, but I'm just going to look at money questions just to start with for the starting few. Right, let's have a look at our next question. Okay, so this question looks very similar. It says Tom and Amy share some money in the ratio 5 to 3, but this time it says Tom gets £70 more than Amy. Work out how much they each receive. So again, let's bring this away from the words. We've got T to A, and it's in the ratio 5 to 3. Now what it says is Tom gets £70 more than Amy. So Tom, who's this one here, is getting a little bit more. Now if we have a look in terms of the parts, look, Amy's getting 3 parts, Tom's getting 5, so Tom is getting an additional 2 parts to Amy. So those extra 2 parts that Tom's getting, it's saying that those plus 2 parts there are worth £70. And from there we can take exactly the same approach that we did on the last one. Okay, we can divide that by 2 to get our value of 1 part. Now again, you could think about this in terms of a picture. We could have Tom's 5 parts, and we could draw 5 little circles, look, and Amy's 3. And then we can just identify in terms of the picture how many more he's getting. Well, he's getting these 2 extra here, so those 2 parts here are worth £70. And again, you can just take a little bit of a logical approach there. Dividing that by 2 tells you the value of each part, and then you can stick your 35 in each of these piles and start to work it out that way. But I'm just going to do it via the numbers. Look, we're just going to divide this by 2, and that tells us that 1 part, which is what we're looking for every time, equals £35. And then from there you can take exactly the same approach we can do for Tom. He's got 5 lots of that, so 5 times 35. There we are, and 5 times 35 is 175. So Tom's getting £175. And Amy, who is getting 3 of those, is going to get 3 lots of 35. There we go, and 3 times 35 is £105. And again, you can add those 2 together to get their total. This one actually doesn't ask for their total, it says how much do they each receive. But if it did, if it said work out the total that they both get, you could actually add those together, look, and we've got 280 as the total. So this question doesn't ask for that, but just thinking about what we could be asked. So we've got Tom gets 175, Amy gets 105, and if it asks for it, we know that they both share £280 between them. So this is following on from what we've just done. It's basically the same as what we've just done. It's just a few more words and sort of all wrapped up in a problem that looks more complicated than it actually is. It says Tom and Adam have a total of 240 stamps. The ratio of the number of Tom stamps to the number of Adam stamps is 3 to 7. Then it says Tom buys some stamps from Adam, and then they have a new ratio. Tom to Adam is now 3 to 5. How many stamps does Tom buy from Adam? Now there's no extra stamps getting added in at any point. We're always having 240. If extra stamps were being added in, this problem does get a lot more complicated, but this type of problem here, look, there's only 240 and they're just sort of interchanging some between them. So if we have our first scenario, look, scenario number 1, we've got 240 stamps and we've got Tom to Adam in the ratio 3 to 7. Now obviously that's 240 stamps shared between them, so the total amount of parts there is 10. So we've got 10 parts equaling 240 stamps. So if we divide that by 10, we get 1 part equals 24 stamps. So if we actually multiply both these numbers, look, Tom and Adam, Tom gets 3 times the 24, and Adam has 7 times the 24. So if we work both of those out, 3 times 24 is 72, and Adam has 7 times the 24, which comes out as 168. There we go. So that's how many stamps they start with, but we've now got scenario number 2, or the second part of this scenario, where Tom and Adam now have stamps in a different ratio. So now it's in the ratio 3 to 5. So now we know it's in the ratio 3 to 5, we can go about splitting these 240 stamps up between them. So we've got 3 to 5, and that is a total of 8 parts. So we've got 8 parts that now equal 240 again. So again, we can divide that by 8, and 240 divided by 8 gives us a total of 30. So this time, one part in this ratio is equal to 30 stamps. So if we have a look, I'm just going to do this in a different colour. We've now got Tom, who's getting the 3 parts, gets 3 times 30, which is going to equal 90, and Adam is going to have 5 of them. So Adam gets 5 times 30, and he gets 150. Right, there we go. So obviously we're looking at, let's have a look at what the question said again. How many stamps does Tom buy from Adam? Well, Tom started with 72, now he has 90. So we can obviously work out the difference there. If we want to show our working out, we can do the 90 stamps that he now has, take away the 72 that he started with, and that leaves us with a total of 18 stamps that he must have bought there. So 18 stamps would be our final answer. And obviously we could have taken that from Adam as well. We could obviously look at the fact that Adam, who's here, started with 168 and then dropped down to 150, which is a loss of 18 stamps as well. So you could look at that in both different ways, but there we go, there's a difference of 18. Okay, so again, there's nothing more complicated in this question. It's just there's a little bit of different wording going on. So it says Maria, Dylan and Kate share £3,000. The ratio of the amount that Maria gets to the amount that Dylan gets is in the ratio 5 to 4. And Kate gets 1.5 times the amount that Dylan gets. Work out the amount of money that Dylan gets. So we want to have a look, how are we actually going to create this ratio? Because at the moment we've got Maria, we've got Dylan, and we've got Kate, but it only tells us the ratio, and that's, let's just highlight that, Dylan and Maria, or Maria and Dylan, 5 to 4. So we've got 5 to 4 for Maria and Dylan, but we don't know how much Kate gets in terms of parts of the ratio. But it does then say Kate gets 1.5 times the amount that Dylan gets. So Dylan gets 4 parts, so if we times that by 1.5, that actually gives us a value of 6. So Kate is getting 6 parts. Remembering multiplying by 1.5, if you don't have a calculator, just adds an extra half on. Half of 4 is 2, add it on gives us 6. So now that we've multiplied that by 1.5, the rest of the question's nice and easy. Because all we're going to do now is split that £3,000 in the question in the ratio 5 to 4 to 6. So if I get rid of this little bit of working out, this times 1.5, let's have a look. In total, that ratio adds up to 15 parts, and now we know that those 15 parts equal the £3,000. So we can find the value of 1 part again by dividing by 15, and 3,000 divided by 15 gives us a value of 200. There we go. So they all get 200. So we can go about timesing them all by 200. We're actually only concerned about Dylan in this particular question, and Dylan gets these 4 parts here. So we can just answer that straight away. Dylan's 4 parts, each one of them's 200 quid. So 4 times 200 gives us £800 for Dylan. There we go, and there is our final answer. And again, you could go about obviously finding out the amount that they all get. We could do Maria times 200, which is 1,000, and Kate's times 200, which is 1,200. And you could even add them all together then and show that there's £3,000 there. But that's how we'd approach a slightly different question here. We've got to think about creating the ratio slightly ourselves. So this question on the screen here, it says only blue vans and white vans are made in a factory. It says the ratio of the number of blue vans to the number of white vans is 4 to 3. And it says for the blue vans, the number of small vans to the number of large vans is 3 to 5. Work out the fraction of the number of vans made in the factory that are blue and large. Okay, so we're looking at these ones that are blue and large. Now, as this sort of question develops and this sort of gets a little bit harder, there's a specific approach that I'm going to take when I'm actually looking at these. And that is I'm going to kind of structure this in the same way that you would structure a probability tree, and looking at this as more along the lines of work out the probability of picking a van that's blue and large out of all of these sort of vans in the factory. And sort of way that I'm going to draw this then is I'm going to draw a bit of a probability tree. So I'm going to start by saying blue to white. Okay, so we've got the vans, they're blue or they're white. Now over here we've got the ratio of blue and white, we've got 4 to 3. Now that's out of 7 in total. So 4 out of the 7 there are blue and 3 out of the 7 there are white. So for the blue here we've got 4 out of 7, and for the white here we've got 3 out of 7. There we go. And then it gives us the next piece of information. Now it only mentions anything to do with the blue vans here, and as these sort of questions develop, we're going to have a look at ones where it mentions something about both branches here. But in this particular question, look, it just says for the blue vans, we've got small and large. So we're only going to do another branch coming off the blue vans here, and that's going to be our small ones and our large ones. And again, we've got a ratio here, it's 3 to 5, so it's out of 8 in total. So for the small vans there, that's the 3, and that's 3 out of 8. And for the large vans there, it's 5, and again, that's 5 out of 8. Now when it comes to actually working out the fraction here that are blue and large, we treat it in the same way that we do a probability tree. We have a look, okay, we go up the blue branch, and we get 4 out of 7 for the blue. And then we go up the large route, or down the large route, depending on how you've drawn it here, and that's 5 out of 8. Okay, and just double check that you've put those in the right place. That's large, 5 out of 8, that's right, so that's blue and large. So all we do normally when we're going along a tree like this is we just multiply those fractions together, and we're not going to do anything different in this question. So all we're going to do is we're going to take that first fraction there for blue, which is 4/7, and I'm going to multiply it by the large fraction there, which is 5/8. There we go. And multiplying fractions is nice and easy. We just times the top and times the bottom. So 4 times 5 is 20, and 7 times 8 on the bottom is 56. There we go, and that's our final answer. 20 out of 56 is our fraction of the vans in the factory here that are blue and large. Okay, so hopefully that makes it quite nice and simple to understand, but essentially we just pair together the two fractions that we're looking at and multiply them together just like we would on a probability tree. We're going to deal with this one here, where we've got y is inversely proportional to d squared, and then we're going to deal with this one here, where we've got d is directly proportional to x squared. So treating it in the same way, let's create a formula for this first one. So y is equal to, and it's inverse proportion, so k over d squared. And then again, we can sub these numbers in. We've got d is 10 when y is 4. So we've got 4, which is y, is equal to k over d squared. And again, the working out to the side, we've got 10 squared, which equals 100. So k over 100. And again, let's rearrange that, so times both sides by 100, so we've got our value for k, and we get k is equal to 400. And again, we can write our formula for that, so let's bring that down here. Let's write y is equal to 400 divided by d squared. Right, there we go, there's our first one done. Let's move on to our second statement here. So d is directly proportional to x squared. So there we go, let's write our formula for that. So d equals k x squared. There we are. And let's plug in those values. So x is 2 and d is 24. So we have 24 equals k times, if I can write that in, times 2 squared. And again, let's do the working out on here. 2 squared equals 4. So k times 4. Or again, let's rewrite that as 4k. So let's get rid of that and write 4k instead. There we go. Okay, so to rearrange that, we're going to divide both sides by 4. So divide by 4, and we get k equals, and we get a value of 6 there. So we go k equals 6, and again, we can rewrite our formula there, but having k as 6. So if we write that down here again, we have got d is equal to 6 x squared. And there we go, there's our two formulas written. Now again, if we just read this question carefully, it says find a formula for y in terms of x. So we have this formula on the left here that says y is equal to 400 over d squared. Now that's a formula for y in terms of d. So we need to replace this d here. And we've got this formula over here that says d is equal to 6x squared. So what we're going to do is we're going to put that 6x squared in place of d. And if we do that, let's see what we get. So we'll get y is equal to 400 over d squared. Now d is 6x squared, so I'm going to put that in a bracket. So 6x squared, and that is going to be squared. Okay, so we're nearly done. Right, we just need to square what's on the bottom there. So y is equal to, we've got 400 on the top, and if we square what's on the bottom, 6 squared is 36, and x squared squared is x to the power of 4, remembering that you just times powers when they're in brackets like that. So there we go, 400 over 36, x to the power of 4. Now again, it does say give it in its simplest form. We're almost done, but the top and bottom here both divide. Now they both divide by, and you might not spot the biggest number straight away, but they both divide by 4. So on the top there, 400 divided by 4 is 100, and on the bottom there, 36 divided by 4 is 9, so 9x to the power of 4. And then that is in its simplest form, 109. Both don't divide by anything similar, so y is equal to 100 over 9x to the power of 4. And to finish this off really, I should get rid of that little step of working out in the middle, so I can write my final answer as y is equal to 100 divided by 9x to the power of 4. And there is our final answer, so let's just highlight that one there. Okay, so this is quite an interesting question because this is talking about density, and obviously we're doing this non-calculator. And normally density is a calculator-based question, so hopefully we're going to have some nice numbers. Now, as soon as you see that word density in a question, you're going to want to write down your formula, whether you use a formula or whether you use a formula triangle. So I'll write down the formula triangle because that works for everybody then. So that's going to be density is equal to mass divided by volume. Now this question says it wants us to work out the mass. So straight away, if I cover up the mass, that means I'm going to do density and multiply it by my volume. So this question gives us a cube, and it says the rubber cube has side lengths of 4 centimetres. So in regards to this image here, we've got 4 centimetres across there, 4 centimetres here, and a 4 centimetre height. So to work out the volume of a cube, you would just multiply all those numbers together, or in other words, 4 times 4 times 4. Obviously take that in stages. 4 times 4 is 16, times that by 4 again, and that is going to be 64. So 64, and the units are centimetres, so it's 64 centimetres cubed. Now it gives us the density. It says the density is 1.5, so we know to do this we do the density, 1.5, and multiply that by the volume, and the volume is 64. So we just need to do 1.5 times 64, which isn't too bad. When you are multiplying by 1.5, that just adds on an extra half. Obviously you can hop the decimal out, you could do the working out to the side. So if we do that, we'll get 64 times 15, 5 times 4 is 20, 5 times 6 is 30, add the 2 is 32. Put our placeholder in, 1 times 4 and 1 times 6 is nice and easy. And if we add that together, 0, 6 and 9, so you get 960, and then you just have to hop the decimal back in one jump as we took it out at the start. So when you jump that in, you get 96.0, so that would be 96, and in the units it said grams per centimetre cubed, so that would be 96 grams as our final answer. So there we go, we'll get 96 grams. So as you can see, we can have density questions that are non-calculator, but you're going to tend to get nicer decimals involved that are just going to be a little bit nicer for your calculations. This question says, in a bag there are red, blue, yellow and green counters. A counter is taken at random from the bag and the table shows the probability of getting each coloured counter. So we've got red, blue and yellow and we're missing green. Then it says later in the question, look, it says there are 45 green counters in the bag. Work out the total number of counters in the bag. So if we have a look here, we just need to figure out what's missing. What's that probability of getting green to start with? Because it's slightly different. It's not saying how many times they're going to pick the counters out or something along those lines. It's actually given us an actual amount of counters allocated to that probability. So at the moment, if we add all of these up, we've got 0.3, 0.25 and 0.15. And they add up to 0.7 or 0.70. There we are, so we're missing 0.3, which again is 30%. There we go. So 30% of the counters are green. And it says down here there are 45 green counters. So this is actually telling us that 30% is actually equal to 45 counters. There we go. So that 30% there is 45 counters. And we need to find out the original amount of counters or the total amount of counters in the bag. And in order to do that, we need to turn that 30% back into 100%. So this is almost like a reverse percentage because we need to break this down in order to turn it back into 100. We can't just multiply it by 2 or multiply it by 3. It's not going to get us to 100%. So if we go about breaking this down, always look, how can we get back to that 10%? And to get 30% back to 10%, we would have to divide that by 3. And that would tell us that 10% is equal to 15 counters when we divide that by 3. There we go, so 10% is 15 counters. And now we're able to turn that back into 100, and from 10% back to 100 is nice and easy because we just need 10 of those, so times it by 10, so that original 100% of the counters is 150. There we go, and there's our final answer. So a slightly different bit of wording there, it actually allocates the amount of counters to that certain percentage. So it's called a reverse percentage, obviously because it's not given us the 100%, it's given us part of it, and it's looking for us to go back or build it back to 100%. Okay, so that's a different sort of approach, a different sort of question. Now when it comes to independent events, we're going to talk about it throughout the video, but an independent event is just two events where the second event is not affected by the first event. And we'll have a look at why it's not affected in these types of different questions, but it's just, that's all that it means there. It just means that the one event that we're looking at is not going to be affected by the other. So let's have a look at this question. Now, in a lot of these questions, you'll normally actually be given a tree, but in none of the ones that I'm going to have a look at, I'm actually going to give the tree. We're just going to draw them all ourselves, because obviously if you're not given the tree, it's important that you're able to do that anyway, and if you are, then that's easier for you. So we're just going to have a look at these slightly harder questions here. So James has a bag of counters, and in the bag there are 4 red and 5 blue, and James takes at random a counter from the bag and notes its colour. He then puts the counter back in the bag, and that's an important bit we're going to discuss there, and takes at random a second counter, and we're going to work out the probability that James takes 2 different coloured counters. So that line there where it says he puts the counter back in the bag, that there is what determines that this is an independent event, because after we take the first counter, if we put one back in the bag, the second time we're just taking a counter from exactly the same bag of counters. So it doesn't actually matter whether we take a red or a blue. So let's have a look at constructing this via a tree. So if we draw a little tree here, we're going to draw 2 branches that represent red and blue. Okay, and that is going to be representing our first pick of the counters there. I'm going to label this part of the tree, so that's the first time we take a counter. Now let's write the probabilities in. So looking over there, we've got 4 red and 5 blue. So in total there we've got 9 counters. So you can do that working out to the side if you want. 4 plus 5 equals 9. So if we're going to write the probabilities here, I'm going to write them as fractions, just keep it nice and easy. Obviously you can write it as decimals if you like, but I think in the case of this question it's probably easier for us to write it as a fraction. So for red it's 4 reds out of 9. So the probability of getting a red is 4 out of 9. And then we've got blue, and that is 5 out of 9. There we go. And just thinking about these fractions here, obviously if you were given the tree and you were you didn't have the information up there and it said that the red was 4/9, you'd have to actually work out the blue there, and obviously the numerators have to add up to whatever that denominator is. If it's 4 out of 9, that tells you there's 9 counters, 4 of them being red, and therefore 5 of them have to be blue in order to make 9 out of the 4 and the 5. So just thinking about that, if you weren't given the the information in the question, you'd have to actually do that yourself on the tree. Now obviously what we have a little scenario here, and I always like to think of it as a bit of a journey. So if we imagine a little person standing over here at the start, not the best drawing there, but we could either go on a little journey. Now we could take a red out of the bag, in which case our little person would end up here, and then we'd have our second counter. So at this point we can construct the second part of our tree, and I'm going to run out a little bit of space here, and this is going to represent the second pick. Now on this second pick here, look at this part of the journey, we've taken a red counter, and now we're going to take another one, and again that can be red or blue. And because the counter's gone back in the bag, again it's going to be 4/9, and it's going to be 5/9 again for blue. And that is that one part of the journey. But of course we might not have taken a red out, so if we get rid of our little person here, and let's imagine that actually instead we've taken out a blue, and we've gone down this part of the journey here, we've taken out a blue counter. So here we are, we've taken out a blue. Now again we're going to take a second counter, okay, and that again can be red or blue, so we'll label that up, red or blue. And again the probabilities are just going to be exactly the same. It doesn't matter whether I took a red or whether I took a blue, it's still 4/9 and 5/9 as that counter has been put back in the bag. So we've constructed our tree, and let's have a look. Let's just get rid of all of this. We now just need to work out this probability, and now the question says work out the probability that James takes 2 different coloured counters. And there are 2 ways that I can actually do that. So to get different colours I could, and I'm just going to squiggle along the lines, and this is how I do it. I go up the red, and then I'd have to take a blue. And the 2 probabilities that you go through on this journey are really important. So we went through 4/9 when we took the red, and we finished on the 5/9. So to work out the probability of that route happening, all we do is we multiply those 2 fractions together, and all you've got to remember is you times when you go across the tree. So if we times them together, we've got 4/9, and we're going to times that by 5/9. And that's really nice and easy. Not to forget, when you're multiplying fractions, you multiply the top numbers. So 4 times 5 is 20, and 9 times 9 is 81. So the probability of getting a red and then a blue is 20 out of 81. Now, not that that one can simplify, but you do not need to simplify fractions when it comes to probability. And the reason being is that that probability there, 20 out of 81, tells us something quite important. It tells us that there are 20 different ways of this happening out of a possible 81 different ways of picking all these counters. That can seem a little bit hard to understand sometimes, but if we labelled the red ones 1 to 4 and the blue ones, let's say 1 to 5, there are 20 different ways of taking a red then a blue. I could take red counter number 1 and then blue counter number 1. Or I could take red counter number 1 and then blue counter number 2, etc, etc. Obviously they're all still red and blue, but if they had different numbers on and we think of them as, you know, all different counters, then there are 20 different ways of doing that. Now what we're going to have a look at now is the other way of getting 2 different counters, because I could take, instead of a red then a blue, and let's think, I'm just going to do a different colour here, I could take a blue and then I could take a red. And that would also give me different colour counters. And again, that goes through these 2 different fractions, so 5/9 and 4/9. And if we times them together, you'll probably notice here that actually we're going to get the same answer because it's the same 2 fractions in reverse. And 4/9 times 5/9, again on the top we get 20, and again on the bottom we get 81. But that there is taking a blue then a red. Okay, and there are 20 ways of doing that as well. So there are 20 ways of getting a red then a blue, and 20 ways of getting a blue then a red. So the total probability there, in order to get our final answer, we just need to add these 2 together to combine them to get the total probability there. So 20 plus 20 on the top gives us 40 out of the possible 81 ways. Remembering you don't add the denominators together there when adding fractions. And that would give us our final answer, 40 out of 81. Okay, so a few different things to be thinking about there. One was constructing the tree, thinking about obviously our first pick and our second pick, and then the next one was obviously multiplying across the tree, and any different combinations that we have at the end, we just add them together and combine them together. Of course, you might get a nice easy question here. It might just say, what's the probability of taking 2 reds? In which case you only need to do the one journey. Have a look at the tree there that goes through the 4/9 and the 4/9. So you just times them together and that'll be your answer. But if there are multiple answers, you just need to think about adding them together at the end. These questions, we've now got some decimals introduced. So not necessarily harder. In fact, you might, depending on which ones you prefer, I personally think they're just as easy as each other, but obviously these are slightly different when we've got decimals involved. So it says Hannah is going to play 1 game of darts and 1 game of snooker, and the probability she'll win at darts is 0.3, and the probability that she'll win at snooker is 0.4. Work out the probability that Hannah will win at least 1 game. Now, win at least 1 game. We'll talk about that in a sec, and let's have a look at how we're going to go about this. But first we need to construct our tree. So looking at this, we've got the first part of our tree could be our first game, and the first game that it mentions is darts, so let's just have darts as our first one. Now we've got in this a scenario of winning or losing, and it says the probability that she will win at darts is 0.3. Now hopefully you already know that probabilities have to add up to 1. Now 0.3 is 30%, so obviously to get it up to 100% or to get it up to 1 is 70% or 0.7. So the probability of losing this time is 0.7. Now we've got the scenario where she's going to play her second game, so she can win or lose. If she wins, then she goes on to play her next game here, which is snooker. Let's label that. Just about fit that in, snooker. And again, it's a win or a lose. And the probability that she wins this game is 0.4. Now again, that's 40%, so 60% to get to 100, or 0.6 to get us up to 1. And that is the scenario there if she wins at darts. She can then win or lose at snooker. So obviously we could lose at darts, in which case, again, she's going to want to go on to play snooker. And again, the probability that she wins is 0.4 and 0.6. It doesn't say that anything changes, It might say in a question, if she wins on the first game or if she wins at darts, then she's got, a higher chance of winning at snooker maybe, but it doesn't mention anything like that in the question. So both of those parts of the branches are just going to be replicated down below. Now it says here, work out the probability she'll win at least 1 game. Now if we have a look at the outcomes at the end of each part of the tree here, we've got this outcome up here, which is a win and then a win. We've got the one below that, which is winning at darts but losing at snooker. We've got the bottom here, which is obviously going down our bottom branch there on darts, which is a lose and then a win. And then we've got a loss and then a loss down the bottom there. Now this language here says win at least 1 game. Now at least 1 game does mean that you could win both. So we could have this route here. Well, that's winning at least one game. Yes, she wins both, and that's definitely at least one. And then we've also got the one below, where she wins one and loses one, and then the one below that, where she loses one and wins one. Now that is the probability of winning at least one game. The only one we don't want is that one down the bottom, losing both. So if we just go ahead and work out all the probabilities here for the top three, then we can get all these probabilities, these different probabilities of winning at least one game. So for the first one there, let's have a look, and I'm going to have three branches here, so I don't want to squiggle all over it. But if we go the win-win, we've got 0.3 multiplied by 0.4, and that is 0.12, 0.12. We've got 0.3 times 0.6 for the one below. And there we go, 0.3 times 0.6 is 0.18. And then the one below that, 0.7 times 0.4, which gives us 0.28. Now there are our three different probabilities, 0.12, 0.18 and 0.28. So just like before, all we need to do is add them all together, and that will give us our combined probability of all those three different outcomes. So you can do them to the side. You've got 0.12, you've got 0.18 and 0.28. And when you add those all together, again, you may or may not have a calculator here. Let's have a look what we get. So 8, 2, 3, 4, 5, 0.58. And there is our final answer, which you can write down here, 0.58 as our total probability. There we go, and let's highlight that. Now obviously that's one way of doing it. There is another way of doing it. Again, we could have actually just worked out the probability of losing both and then subtracted that from 1. Now obviously that introduces another method here, thinking about obviously just eliminating the one that we don't want, but that is another method that you could have done as well. I'm thinking about how that works. If we'd have done the probability of a loss and then a loss, that would have been 0.7 times 0.6, which is 0.42, and you can do 1 take away 0.42, which would leave us with what's left over, which is 0.58. Okay, so you can do that. It's a little bit quicker, but obviously if you just want to follow the same method and just work out all the roots of the ones you want, then just follow this same approach here and just pick out the ones you want, showing all you're working out. Okay, so looking at a cumulative frequency graph, when we have to draw one of these, the first thing you want to have a look at in the table is if this word here says frequency or cumulative frequency. So as it says frequency, we're going to have to actually find the cumulative frequency, which we can do just by adding up as we go down the rows. So we start with 4, then we get an additional 18, that takes us to 22. Then we've got an additional 24, so that's going to take us to 46. And an extra 40 there, so that's 86. Adding on an extra 24 gets us to 110. And then we finish off with the extra 10, which finishes on 120. And that's good because that matches up to the top of our axes there when we have that 120. Now when we're plotting one of these, we're just going to plot against the n numbers, so those n numbers there on the intervals, and that means just plotting it on the graph. So we've got 10 and that goes up to 4. Now this is obviously quite small on my screen, but you just need to plot it as accurately as you can. So I'll try and do it as best as I can, but this should give you a good idea. And then we've got 22 as our cumulative frequency. We're going to plot that against 20. So I'm going to go just above 20 there for the actual value, so just on 22. 30 goes up to 46. Again, I'll try and do that as accurately as I can. 40 goes to 86. There we go. And 50 goes to 110. Which is a bit easier to plot, and then 60 goes to 120, which is right at the top. So when you are joining these up, make sure you look at the starting number, which in this case is 0. So we're going to go from 0 with a nice smooth curve through all those points, not using a ruler, and there is our cumulative frequency graph drawn. Now for part B in this question, it says to find an estimate of the interquartile range, and it wants us to use the graph for that. So when we're finding an estimate of the interquartile range, we need to obviously find the quartiles. So if we look at our total, which is 120, and then we divide that by 4 to find the quarter, each of the quartiles is going to be 30 above the bottom and 30 down from the top. So if we find 30 on our axes, and again you can do this a lot more accurately when you have the paper in front of you, but that is 30 just there. I'm going to go across to my curve, and then I'm going to go down. I'm going to read the value as accurately as I can. So that for me comes out as 23, and that is my lower quartile. I'm then going to do the same from the top, so go down 30 from the 120, that's going to be down at 90. and I'll go across again to my curve using a pencil and a ruler, and then go down again as neatly as you can, and I am going to land there on 43. Okay, so I've got my values. I have my upper quartile, which has come out as 43, my lower quartile, which has come out as 23. So to get the interquartile range, we just do 43, take away 23, and that leaves me with an interquartile range of 20, and that would be my final answer, and that's how I go about finding the interquartile range. So it says here there are 10 boys and 20 girls in a class, and the class has a test. It says the mean mark for all the class is 60 and the mean mark for the girls is 54. Work out the mean for the boys. So when it comes to a question like this, obviously we know, or hopefully we know, that when we're normally working out a mean, we get the total, we divide by how many people there are or how many things there are, and we get our mean. Okay, so we do the total and we divide by the amount, okay, for whatever it is. There we are, on its most basic sense there with the mean. You do the total divided by the amount. Well, in this question here, obviously it doesn't actually give us the total. It tells us what the mean is, it tells us the amount, it tells us that there are 10 boys and 20 girls, but it doesn't actually tell us the total. So what we're going to do is we're going to go backwards to work out some of these totals, okay? So we're going to think about this in reverse. All right, and that is how you get the mean there, the total divided by the amount. Okay, so if we link some of these things up, then it says that there are 10 boys. It doesn't give us the mean for the boys, so that's no good so far. So that first piece of information that we are actually given in terms of the mean, it says the mean mark for the whole class is 60. Well, if we were going to work out the mean for the whole class, we'd get their total. Let's call that X. We divide it by the amount, and in this case the whole class, well, there's 10 boys and 20 girls, so we would divide it by 30, and it would give us this mean here, which it says is 60. So in other words, we're looking for a number that divides by 30 that gives us the answer 60, and we can just do that in reverse. We can just do 60 times 30. So actually all we're going to do in these questions is we're going to link the mean that we're given with the amount that is appropriate for that mean. So I'm going to get rid of this little bit of algebra that I've drawn here, but obviously you could think of it in terms of an equation, but this is the sort of concept that we're going to run throughout this question, and hopefully once you actually get your head around this and why we multiply instead of divide, obviously we are doing a reverse. This question obviously becomes a lot easier then. Okay, so obviously thinking about this topic's actual name, it's called a reverse mean. Normally when you work out the mean, you do a divide, and obviously then the opposite or the reverse of dividing is multiplying, and in these questions we're going to be multiplying rather than dividing to go backwards. So let me get rid of that. So let's have a look. So obviously we've been given that the mean for the whole class is 60, and we've just established that there's 30 students or 30 people in the whole class. So we're going to do 60 times by those 30 students, and that's going to tell us their total. So 6 times 3 is 18, add on the 2 noughts, that's 1,800, and that is the total for the whole class. And it's usually worth just labelling these, particularly if you haven't quite got your head around it. Let's just label that total for class. There we go. Right, so the next bit of information then, we've also been told that the mean mark for the girls is 54. Now, in terms of the question, look, there are 20 girls. So if there's 20 girls and their mean is 54, we'll take their mean, 54, times it back by that 20 to find out what their total was. So 54 times 20, there we go, and that gives us 1,080. And there we go, there is the total for the girls. And let's just label that again. Total for girls. Right, so just thinking logically about the information that we've got here, we've got a class of boys and girls. It says the total for the class is 1,800, the total for the girls is 1,080. So logically we can work out now the total for the boys, we can subtract those away from each other. So 1,800, take away 1,080, and let's write that down. There we go, take away 1,080, leaves us with 720. There we go, and that's the total for the boys. Let's label that up, total for boys. And now we can go about answering the question, because now we know the total for the boys, we can actually think about working out their mean, and that's what the question wanted. It said work out the mean for the boys. So we've got the total for the boys is 720, and in total up here we were given in the question, let's highlight it in the same colour, there are 10 boys. So to work out the mean, just like normal, we would just finish this off by saying the total for the boys is 720. I'm going to divide that by how many boys there are, which is 10, and that gives us a mean of 72. There we go, and there's our final answer. I'm just thinking about what we did there, just working backwards through the question, multiplying the means by the amount to get the totals, and then using a bit of logic there to find out therefore what the total for the boys must have been, and then just working out the mean as normal. Okay, that is the end of this video looking at paper 1. Don't forget to have a look in the description if you want to have a look at papers 2 and 3. Don't forget to download the checklist so that you've got something just to give you a bit more advice on some topics to have a look at. Again, don't forget that this is not all the topics or just one variation of each topic within this video, so you do need to do some further research, have a look more into your revision books and what your teachers are giving you in terms of in your lessons, and obviously make sure that you are looking at the full videos on each and every topic that you're not 100% confident on. So there we go, I hope that was useful and helpful. If it was, don't forget to like, don't forget to comment, don't forget to subscribe, and I'll see you for the next one.